The nearest star isn't a destination, it's a sentence, written in years of radiation, crushing energy demands, and a ship that must become a sealed, living world. For a century we've been promised the stars, yet every honest calculation makes the dream feel less like engineering and more like faith. So are humans actually capable of reaching another star on any meaningful timescale? Or does the universe forbid it in plain physics? A starship is not a vehicle, it is a verdict, delivered by arithmetic that does not care who is dreaming. Between one sun and the next lies a gulf where every shortcut becomes a bill, and every bill demands a payment in lives. Tonight we step past the posters and the promises into the ledger where interstellar travel is actually recorded. Out there, distance is not a backdrop, it is the first antagonist, stretching every plan into a multi-generational wager. Speed looks like salvation until you price it honestly. Then velocity becomes a tyrant with compounding interest, and any mission that hopes to arrive must also learn to stop, because a flyby is not a home. We will follow the problem as it hardens from romance into engineering, and from engineering into biology. A ship crossing interstellar space must endure impacts with what seems like nothing, yet behaves like a storm at high velocity. It must carry shielding, power and repair capacity for decades, while its instruments and computers age in silence. And inside the hull, a closed world must keep breathing. Carbon, nitrogen, water, microbes, crops, and people cycling through limits that do not forgive drift. This is not a story about discouragement, it is a story about scale, and about what scale demands. The same physics that makes starflight conceivable also makes it uncompromising, forcing us to ask what meaningful timescale really means for human bodies, human societies, and human patience. If we insist on a shortcut, we will find only slogans. If we accept the full cost, we may find a path. Across this journey, we will measure the true price of distance, the tyranny hidden in the rocket equation, and the energy that must be found or built. We will confront the paradox of deceleration, the hazards of the interstellar medium, and the fragile reality of self-sustaining ecosystems. And we will look, without flinching, at the most difficult payload of all, the human mind and body, asked to remain whole across years that feel like an era. By the end, the stars will not seem closer, but our understanding of what it takes to reach them will be sharper, cleaner, and strangely more beautiful. Because when hype falls away, awe does not disappear. It matures into responsibility, and into a clearer sense of what we can build within the reachable universe. Before we begin, let us know in the comments below where in the world you're watching from, and what time it is there. Now settle in for a journey. We begin with the nearest star and the scale we keep underestimating, then descend through 5 hard limits, one by one. Along the way, celebrated solutions will face the fine print, and the horizon will change without moving. We grew up on a promise that the stars are the next neighbourhood over, close enough to visit between commercial breaks. In stories, a ship lifts off, jumps to warp, and arrives by the next scene. The travel time is a plot detail, not a physical bill. Cinema rarely lingers on propellant mass, radiation dosage, or the slow drift of years. The camera cuts from launch to arrival, and our brains accept the cut as destiny. We inherit a quiet assumption that the universe is vast yet somehow conveniently traversable. That promise is seductive because it feels like progress, and progress is one of our favourite myths. It suggests that distance is just an engineering problem we have not solved yet. It frames interstellar flight as inevitable, like aviation after the first balloon. But aviation did not defeat distance by ignoring the atmosphere's rules. It succeeded by exploiting them, and by paying the full price in fuel, infrastructure, and safety culture. Interstellar travel asks us to do something similar, except the medium is almost nothing at all. Now collide that story with one number and let it land without music. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. Light-years sound poetic, but they are a measure of how far reality can stretch. Proxima is a small, cool red dwarf in the Alpha Centauri system, faint to our eyes and invisible without instruments. It is close by cosmic standards, the way the next town is close on a continent. Yet even this nearest neighbour sits across an ocean of vacuum that dwarfs every human journey. A light year is the distance light travels in a year, moving at 219,792 kilometers per second. Light does not accelerate like a rocket, because it is already at nature's speed limit. Multiply that by 4 and change, then ask what any human machine can do. The gap between those speeds is where the dream starts to strain, and where honest narration has to slow down. When we say only a few light years, we are smuggling in a misunderstanding about what few means. 4 light years is not a short trip, it is a statement about time itself. Our fastest spacecraft are not science fiction ships, and they do not glide on invisible fields. Voyager 1 is a real object, built with 1970s electronics and a gold record bolted to its side. It is still moving outward at roughly 17 kilometers per second. That is about 61,000 kilometers per hour, which sounds fast until you compare it to light. At that speed, a trip across Earth takes minutes, and a trip to the Moon takes days. But interstellar space does not care about human scales, and it does not reward bravado. At Voyager 1's pace, reaching Proxima would take on the order of 75,000 years. That is not a mission timeline, it is a geological interval. It is longer than all of recorded human history. 75 millennia is older than agriculture, older than cities, older than writing, older than the first bronze tools. It spans ice ages and coastlines shifting, languages blooming and vanishing, and entire civilizations rising and collapsing into dust. A spacecraft coasting that long is not a vehicle anymore. It is an artifact drifting through epochs. Even if you cut that time by 100, the trip remains centuries, long enough for nations to appear and disappear. Even if you cut it by 1,000, the trip still outlasts a human life. The nearest star is not nearby in any sense that matters. And notice what those cuts imply, because the arithmetic hides a demand. Cutting travel time by 1,000 means going 1,000 times faster, and speed is never free. Every extra kilometer per second must be purchased with energy, mass, and engineering that survives the consequences. So we need a translation layer, because 4.24 light-years is too abstract for intuition. Numbers that large slide off the mind like water off glass. We need a ladder of familiar distances, rung by rung, until the scale becomes felt. Start with the distance from Earth to the Sun, 1 astronomical unit, the baseline of our daily sky. Sunlight takes about 8 minutes to reach us, which is already a reminder that space has scale. When you look at the Sun, you're seeing it as it was 8 minutes ago. 8 light minutes feels manageable because we live inside it and our lives evolve to fit it. We orbit in it, communicate in it, and navigate within it. Yet even that small slice of light travel time hides a vast emptiness between two bodies that look adjacent in the sky. If you could shrink the Earth to a peppercorn and the Sun to a grapefruit, they would still sit meters apart. Between them there would be nothing to breathe, nothing to push against, and almost nothing to collide with. Space is not crowded, it is mostly absence, and that absence is the medium of every mission. Now step outward to the planets and watch the sunlight lag behind your imagination. Light takes minutes to reach Mars, and it can take more than an hour to reach Saturn. Light takes hours to cross the outer solar system, depending on where the worlds are in their orbits. That delay is not just trivia, it is operations. When engineers send commands to distant probes, they wait for the signal to crawl across the void, and they cannot correct mistakes in real time. The solar system is not a tight cluster, it is a sparse architecture. Even within our own neighbourhood, the distances are so large that spacecraft often travel for years before they arrive. A mission to Jupiter is a long-haul expedition, not a weekend flight. The planets are islands, and the sea between them is mostly black. Then step beyond the planets to the Kuiper Belt, where icy bodies circle in the dark like embers that never ignite. Light takes more than half a day to reach those distances. Human probes take years, and they still feel like they are crawling. On screen, the Kuiper Belt is often drawn like a neat ring, but reality is messier and thinner. Objects are separated by millions of kilometers, and most of the volume is empty. A spacecraft crosses it the way a needle crosses fog, moving through a region without ever seeing most of what is there. Keep stepping to the heliopause, where the sun's influence thins into interstellar space. The solar wind, a stream of charged particles, slows as it meets the pressure of the interstellar medium. Voyager 1 took more than 3 decades to reach that boundary. It did not arrive at a wall, it crossed a gradient. That gradient is subtle, measured in particle counts, magnetic fields, and faint changes in plasma waves. To a human eye, nothing would look different. because space is already dark. Yet for physics, the heliopause is a real frontier, the edge of a bubble blown by our star. And then there is the Oort cloud, the hypothetical reservoir of comets far beyond the known planets. Its inner edge may be thousands of astronomical units away, and its outer edge may be a significant fraction of a light year. We infer it from the orbits of long-period comets, which arrive from every direction like messengers from deep time. If the Oort cloud is real in the way we think, then our solar system is not a tidy disk. It is a small star system wrapped in a vast, cold halo. Even that halo is still not the next star. Pause on that image, because it changes the emotional geometry of space. Our planets are a thin, bright stage near the sun, while the Oort cloud is a dim cathedral of ice surrounding everything. And beyond that cathedral's last stones, the true interstellar gulf begins. Because after the Oort cloud there is more emptiness, and the emptiness is the point. There is no highway, no lane markers, no convenient refueling stations. There is just interstellar medium, thin enough to be called a vacuum by any earthly standard. That medium is not perfectly empty, and that detail matters at high speed. It contains stray atoms, dust grains, and magnetic fields stretched across light years. At a significant fraction of the light speed, even a dust grain becomes a projectile, and even a rare atom becomes a source of erosion and radiation. The dominant feature of space is not planets or stars, because those are the exceptions. The dominant feature is distance, expressed as time, risk, and energy. Interstellar travel is mostly travel through nothing. This is where hype usually tries to rescue the story, because emptiness feels like an insult to narrative. It offers a new engine, a clever trick, a breakthrough around the corner. It treats physics like a temporary obstacle, waiting to be negotiated. Historically, this pattern is familiar, and it has cycled for more than a century. Early 20th century magazines promised atomic rockets and fast interplanetary liners, and later decades promised fusion drives and effortless warp. Each era projected its newest power source onto the same old desire to make distance stop mattering, but physics is not a villain, and it is not negotiable, even when the dream is sincere. It is the rulebook that makes stars shine and rockets fly. If we want honest awe, we have to start with the constraints. This documentary is anti-hype and pro-physics, which is another way of saying pro-reality. The goal is not to kill wonder, but to replace wishful timelines with real ones. The goal is to understand what the universe charges for crossing interstellar space. That charge is paid in energy, in mass, in shielding, in redundancy, and in the slow accumulation of failure probability. It is paid in the engineering of systems that must run without rescue, and in the psychology of crews who cannot simply turn back. If we ignore the bill, we do not get a discount, we get a disaster. To do that, we will return to 5 hard limits again and again as our narrative spine. They are distance, the rocket equation and energy, the deceleration paradox, closed ecosystem fragility, and human cargo across generations. Each limit is survivable in theory, but brutal in combination. Distance is the first limit because it multiplies everything else, like a lever that magnifies cost. It multiplies exposure time, system redundancy, and the chance of failure. It multiplies the amount of energy you must carry and the amount of patience you must demand. Distance also multiplies communication delay, which reshapes control and trust. A crew cannot rely on Earth for moment-to-moment guidance when signals take years to cross. Even a robotic probe becomes, in practice, an autonomous civilization of software and hardware making decisions alone in the dark. The second limit is the rocket equation, which turns speed into a tyrant with clean handwriting. To go faster, you need more propellant, which increases mass, which demands even more propellant. The math is not pessimism, it is bookkeeping. The rocket equation is ruthless because it links your final speed to the ratio between your starting mass and your ending mass. If your engine throws propellant out faster, you gain leverage, but the propellant still has to be carried at the start. Every tank you add becomes something else you must accelerate, and the spiral begins. Energy is tied to that equation, and the numbers escalate quickly once you stop thinking in everyday units. Kinetic energy scales with the square of velocity. Doubling speed quadruples the energy you must supply, and it also quadruples the energy you must later remove. At interstellar speeds, energy is not just a number on a chart, it becomes heat, stress, and radiation. Power system must run for long durations, and waste heat must be rejected into space through radiators. Space is cold, but it is also insulating, and dumping heat is harder than it looks. That leads to the third limit, the deceleration paradox, which hides inside every optimistic travel time. Getting to another star is not just about arriving near it. You must also slow down enough to do anything meaningful when you get there. Acceleration gets the headlines, but deceleration is where missions become real. If you arrive too fast, you cannot map a planet carefully, you cannot deploy landers safely, and you cannot respond to discoveries. You will have crossed the gulf only to glance at the prize and lose it behind you. A flyby at a significant fraction of light speed is not exploration, it is a blur. If you cannot brake, you cannot orbit, land, or linger. The destination becomes a drive-by, and the science becomes a snapshot. Braking is difficult because there is nothing to push against in deep space, and carrying extra propellant for braking triggers the rocket equation again. You can try to use the destination star's light or magnetic environment, but those forces are weak at the distances where you need them most. The paradox is simple. You must bring your stopping method with you. The fourth limit is ecology, because a starship is a tiny world with no outside. It must recycle air, water, and nutrients for years, decades, or centuries. Closed systems fail in subtle ways, and small imbalances compound over time. A closed ecosystem is not a sealed jar with a plant, because humans are noisy biological machines. We shed microbes, we produce waste, we require varied nutrition, and we carry complex microbiomes that interact with the habitat. In a closed loop, a minor contamination or nutrient drift can become a slow, mission-ending cascade. We have never run a truly closed ecosystem for a human crew at the scale and duration required. We have run partial loops, resupply chains, and controlled habitats. Interstellar travel demands a self-sustaining biosphere in a metal shell. Even on Earth, ecosystems are stabilized by vast buffers, oceans, soils, and seasons that dilute shocks. A ship has no such luxury, only tanks, filters, and carefully managed bioreactors. The question is not whether recycling is possible, but whether it is reliable for decades without external rescue. The fifth limit is human cargo, because people are not instruments that can be powered down and stored. Humans age, suffer, reproduce, and change culturally. A mission that lasts longer than a lifetime becomes a generational project, with ethical and social questions that engineering cannot solve. If you launch children who will die before arrival, what does consent mean? If you plan for births en route, what does mission discipline mean? If you expect multiple generations to maintain a ship, what does governance become? A multi-generation crew is not just a technical challenge, it is a living society under pressure. Education becomes mission-critical because skills must be transmitted without drift. Culture becomes a system parameter because boredom, conflict, and meaning can shape survival as much as oxygen and water. These limits are not arguments for giving up, and they are not a sneer at ambition. They are arguments for clarity about what we are really proposing. A plan that ignores them is not optimistic. It is fictional. So why does this matter beyond the romance of starflight, beyond posters of sleek ships crossing neon galaxies? It matters because big dreams shape budgets, and budgets shape what gets built. If the public is sold easy star travel, disappointment can turn into distrust. That distrust has consequences because science and engineering depend on long-term credibility. When promises are inflated, the eventual correction feels like betrayal, even when the correction is just arithmetic. A culture that learns to distrust space claims may also distrust quieter, more achievable missions that deliver real knowledge. It also matters because our own solar system is full of reachable frontiers, and they are not consolation prizes. There are moons with oceans, asteroids with resources, and planets with histories written in rock. If we misjudge interstellar travel, we may neglect achievable exploration. The solar system is still a laboratory of origins, chemistry, and potential habitability. It contains environments that challenge our definitions of life, and it offers stepping stones for technology that could someday matter for the stars. The point is not to retreat, it is to sequence our ambitions intelligently. Honest constraints can sharpen priorities rather than shrink them, and they can make wonder more durable. They can push us toward technologies that help near-term missions, while still informing long-term ambitions. They can keep wonder grounded in reality, where it can survive scrutiny. The central question is simple and uncomfortable, which is why we keep trying to decorate it. Are we physically capable of sending humans to another star within any meaningful timescale? Or do distance, energy, braking, ecology, and biology turn interstellar travel into a beautiful but unrealistic dream. We have been promised the stars for a century, in magazines, speeches, and movies, and the promise has shaped generations. Yet every time we do the math, the universe feels less like a frontier and more like a verdict. Interstellar travel starts to resemble a belief system, but belief is not the only option, and skepticism is not the enemy of awe. We can replace slogans with numbers and still keep the wonder intact. We can admit that the nearest star is far and still ask what is possible. In the chapters ahead, we will measure the distance properly, then price the energy properly, then confront the problem of stopping at the destination. We will test whether closed ecosystems can endure and whether humans can endure with them. We will keep returning to the same constraints because repetition is how reality teaches. For now, hold on to the scale, because it is the foundation of everything that follows. Proxima is 4.24 light-years away, and Voyager's pace would take roughly 75,000 years. That single comparison resets the entire conversation. Once the scale is real, the engineering questions become sharper, not softer, and the trade-offs become visible. What speed would make the trip meaningful, and what would it cost? What would it take to accelerate, coast, and brake without breaking the mission? The nearest star is not nearby, but it is not unreachable by imagination, and imagination is where planning begins. The brutal reality is that imagination must submit to physics, and physics will be our guide as we begin with the first limit, distance itself. Distance is not a mood in spaceflight. Distance is a schedule, a risk curve, and an energy bill. On a star chart, it looks like a clean gap, but in engineering, it becomes a stack of compounding obligations. Chapter 1 left us with one stubborn fact. Proxima Centauri is 424 light-years away, and light defines the unit. A light-year is not time, it is length, about 9.46 trillion kilometers traced by a photon in 1 year. In the night sky, Proxima hides in the glare of its brighter neighbours. It is a small red dwarf, dim to human eyes, yet gravitationally close by cosmic standards. That closeness is deceptive, because nearby in astronomy still means crossing an ocean of vacuum. Now, we translate that poetic number into mission time. We build a ladder of speeds, then watch the years stack up. The ladder is simple arithmetic at first, and then it turns into a moral question about what counts as a human project. Start with a speed that sounds impressive in everyday life. 1,000th of light speed is 0.01 c, about 300 kilometers per second. On screen, the number looks heroic, 300 kilometers every second. Yet the star barely seems to move. That is faster than any spacecraft we have ever flown. Voyager 1, the fastest object to leave the solar system, cruises at only about 17 kilometers per second relative to the Sun. Even the Parker Solar Probe, diving deep toward the Sun, peaks around 200 kilometers per second near perihelion. So 0.001 c is already beyond our proven deep space cruise speeds. It is also slow enough that Proxima becomes a multi-millennial destination. The math is brutal because the distance is fixed, and the numerator never negotiates. At 0.001 c, 4.24 light-years takes roughly 4,240 years in Earth time. Add launch windows, course corrections, and failures, and the number only grows. Add the reality of acceleration and deceleration, and the cruise time is no longer the whole story. A 4,000-year mission is not exploration in any human sense. It is a message in a bottle, aimed at a civilization that may not exist. It assumes institutions that outlive empires, languages that outlive cultures, and maintenance philosophies that outlive the very idea of mission control. Even if the payload were robotic, the timescale changes the meaning of success. You're not sending a probe to be celebrated, you're sending it to become an artifact. It becomes a time capsule launched into a future that cannot promise to remember you. Move up one rung to 0.1 c. That is about 3,000 kilometers per second, 10 times faster, and still far beyond current propulsion. It is the kind of speed that makes chemical rockets look like fireworks, bright, brief, and fundamentally mismatched to the job. At 0.01 c, the trip time drops to about 424 years, ignoring acceleration and braking. That is shorter than 4,040. But it is still a civilization-scale commitment. It is long enough that the people who launch would be historical footnotes to the people who receive. 4 centuries is longer than the age of modern science. It is longer than the time between Newton and today, and it demands continuity across revolutions. It also demands that the mission's goals remain meaningful after centuries of scientific change. Think about how instruments evolve in just one lifetime. A telescope from the early 20th century is not merely outdated, it is conceptually surpassed by new detectors and new questions. A 424-year probe risks arriving with yesterday's tools to answer tomorrow's problems. Now take the speed that often appears in optimistic proposals. 1/10 of light speed is 0.1 c, about 30,000 kilometers per second. At that velocity, the ship is no longer a spacecraft in the familiar sense. It is a fast-moving physics experiment. At 0.1 c, Proxima is about 42.4 years away in the Sun's frame. Again, before we pay for speeding up or slowing down. In visuals, the timeline finally looks like something you can place on a calendar. It tempts you into thinking the hardest part is behind you. 42 years sounds like a career, and that is the trap. A career assumes resupply, rescue, and a stable world behind you. Interstellar flight offers none of those assumptions, and it punishes the habit of thinking in short operational loops. Even if a crew survives the trip, the mission must survive decades of micrometeoroids, radiation exposure, component aging, and software drift. The vacuum between stars is not empty. It is thinly populated with dust grains and high-energy particles. At 0.1 c, even a speck of dust carries the energy of a bullet. Materials fatigue becomes a slow, invisible antagonist. Polymers embrittle, lubricants outgas, solder joints creep, and cosmic rays flip bits in memory. You can design redundancy, but redundancy itself adds mass, and mass raises the energy bill. This ladder is the first tension point. The speeds that make timelines human are far beyond anything we can currently accelerate, power, or protect. The gap is not a missing gadget, it is a missing industrial capability at an entirely different scale. It also exposes a common rhetorical dodge. People say we only need to go faster, as if speed is a dial. But speed is not a dial you turn, it is a debt you take on, paid in energy, mass, and risk. Speed is not a dial. Speed is a demand that multiplies energy, multiplies shielding requirements, and multiplies the difficulty of stopping at the end. Every additional kilometer per second changes what the environment means, because the environment's particles hit you harder. Before we even discuss fuel or braking, distance already forces a choice. Either we accept missions that outlast lives, or we chase velocities that punish physics. That choice is the universe's first no, delivered without malice and without exception. To keep the math honest, we need to say what these speeds mean in engineering terms. 0.1 c is not 10 times harder than 0.01 c. It is far more costly, because the underlying scaling laws are not gentle. Kinetic energy scales with velocity squared. If you multiply speed by 10, you multiply energy by 100, and you must also remove that energy to stop. The same physics applies to every kilogram you carry, including shielding, habitats, and spare parts. So the ladder is not linear, it is a cliff disguised as a staircase, and the higher rungs are not just faster, they are violently different. When a vehicle moves at 0.1 c, it is carrying a stored catastrophe if anything goes wrong. On screen, imagine a clean line of numbers turning into a steep curve. The graph looks calm at low speeds, then it bends upward as if pulled by gravity. That bend is not a graphic choice, it is the shape of the universe's accounting. Now add the piece that science fiction often uses as a consolation prize. Relativity is real, and time dilation can reduce the crew's experience travel time. It is one of the most beautiful truths in physics, and it also refuses to be convenient. But relativity does not hand out discounts at modest fractions of c. The universe only bends time dramatically when you approach light speed closely. At low fractions of c, Newton's intuition remains stubbornly accurate. The key number is gamma, the Lorentz factor. Gamma tells you how much time slows for the moving traveller compared to Earth. It is defined as 1 divided by the square root of 1 minus v squared over c squared. That formula matters because it hides a cliff of its own. At small v, gamma barely moves from 1, and the effect is tiny. Near c, gamma rises sharply, and the cost of each additional fraction of c becomes extreme. At 0.1 c, gamma is about 1.05. That means the crew experiences about 0.5% less time than Earth does. 0.5% sounds like a rounding error, and and on a decades-long mission it mostly is. 0.5% of 42 years is only a few months. Time dilation is real, but it does not rescue a mission that is already decades long. The ship's clocks tick a little slower, yet the crew still grows older in the ordinary way. At 0.01c, gamma is essentially 1.2005. The difference is days across centuries, which is irrelevant to biology and logistics. Your bones, your cells, and your psychology do not care about shaving a handful of days off 400 years. Even at 0.5c, gamma is only about 1.15. You would still experience most of the trip, and you would still need extraordinary propulsion and shielding. The romantic image of relativistic travel does not begin at half-light speed, it begins much closer to the limit. To cut a 42-year Earth-frame trip down to something like 10 years of crew time, you would need gamma around 4. That implies speeds above 0.6c. At that point, you're not merely fast, you're operating in a regime where energy requirements become almost surreal. That is the non-intuitive consequence of relativity. The dramatic effects live near the limit, where every additional fraction of c costs disproportionate energy. The closer you get, the more the universe charges you for the privilege. Relativity also adds a second twist. From Earth, the ship's clocks run slow, but from the ship, the distance to the destination contracts. Space itself, along the direction of motion, becomes shorter in the traveller's frame. Both views agree on the outcome. You can trade time for energy, but only by paying for extreme velocity, and extreme velocity makes every other limit harsher. The same gamma that shortens the cruise trip also raises the intensity of radiation in their frame. So time dilation is not a loophole. It is a reminder that the universe has a speed limit, and that approaching it is expensive in every sense. The speed of light is not a suggestion, it is a structural feature of reality. Distance also breaks another comforting assumption. Even if you could go, you cannot stay connected to home in any normal way. The nearest star is still far enough away to fracture the idea of conversation. Communication is limited by the same speed of light that defines the distance. Signals do not care about hope, and they do not arrive early. A radio beam is still a stream of photons, and photons obey the same limit as everything else. Proxima is 4.24 light-years away, so any message takes 4.24 years to arrive. A reply takes another 4.24 years to return. Even a simple yes or no becomes a decade-long exchange. That is an 8.5-year round-trip conversation, and that is the best case when both sides are alive and listening. It assumes the transmitter is working, the antenna is pointed correctly, and the power system has not degraded. During cruise, the delay grows as you recede from Earth. Operational control becomes planning, autonomy, and trust in systems that cannot ask questions quickly. The mission plan must be written like a constitution, not like a checklist. For a human crew, the delay is psychological. There is no real-time help, no immediate comfort, and no quick correction from mission control. The voice of home becomes a recorded memory, arriving years after the moment that produced it. For a mission architecture, the delay is structural. You must design for local decision-making, local repair, and local governance, because Earth is always years behind. Even routine disagreements become existential, because arbitration cannot happen on human timescales. Even arrival does not end the isolation. When the crew reaches Proxima, Earth is still 4.24 years away by radio, and the crew is still alone. The first images they send home will be history by the time anyone reacts. There is also a quieter implication for science. If the crew discovers something unexpected, an atmosphere, a hazard, a new target, Earth cannot redirect them in time. The explorers must be the planners, because the planners are trapped in the past. Distance also reshapes navigation in ways that are easy to underestimate. In interstellar space, a tiny pointing error becomes a huge miss. The sky is no longer a backdrop. It is a coordinate system you must measure with relentless precision. Imagine leaving the solar system with an angular error of 1 arcsecond. That is a small fraction of a degree, and it is hard to see without instruments. It is roughly the apparent size of a coin seen from kilometers away. Over 4.24 light-years, that error can translate into a miss measured in astronomical units. You can sail past the target system without ever seeing it up close. The destination could remain a bright dot, never resolving into a world. Even if you aim correctly, you must track your position over decades. You must measure star fields, pulsar timing, and inertial drift, then update your trajectory. Navigation becomes a slow dialogue between sensors and models, repeated thousands of times. Star trackers compare patterns of light against catalogues, looking for tiny shifts. Pulsars offer a kind of celestial lighthouse, with pulses that can act like a galactic clock. In plain terms, you are triangulating in a dark ocean using distant flashing beacons. Navigation is not just knowing where you are. Navigation is having the ability to change where you will be. Knowledge without control is just a post-mortem. Course corrections require delta V, which means propellant, power, and engine reliability. Every correction is a trade between precision and mass. If you carry more propellant for corrections, you must accelerate more mass in the first place. Interstellar trajectories also face a moving target. Proxima is not parked in space, and neither is the Sun, and their relative motion matters over decades. Both stars orbit the Milky Way, and both carry their own small motions through the local stellar neighbourhood. You must aim not at where Proxima is today, but where it will be when you arrive. That prediction must survive uncertainties in acceleration, drift, and system performance. It also must survive imperfect knowledge of the star's exact motion, refined only by ongoing astronomy. At 0.1 c, a one-year timing error is enormous. You could arrive tens of billions of kilometers off the intended approach corridor. In visuals, the target window shrinks to a thin ribbon, while the ship's uncertainty swells like a fog. So distance is not just time. Distance is navigational fragility, because the longer you fly, the more small errors accumulate into mission-scale consequences. A tiny bias in a sensor, repeated for decades, becomes a miss you cannot afford. This is where the phrase "just go faster" collapses. Faster reduces exposure time, but it increases the penalty for mistakes and the energy of every collision. It also increases the demands on guidance, because small timing errors translate into larger spatial errors, and faster does not eliminate the need to brake. If you want to do science, rendezvous, orbit, or land, you must arrive slow enough to stay. A flyby at 0.1 c is not a visit, it is a blink, data gathered in hours after decades of travel. Even if we postpone braking to a later chapter, distance forces the preview. Any speed that makes the trip short also makes stopping brutally hard. You must shed almost the same kinetic energy you paid to gain, and the universe does not offer free breaks. So the distance problem is not solved by optimism. It is solved by a coherent plan that includes acceleration, navigation, communication, and arrival conditions. Each element is chained to the others, and distance tightens every link. We can now restate the central question with sharper edges. Are we physically capable of sending humans to another star within a meaningful timescale, without turning the mission into a generational gamble? That question is not pessimism, it is due diligence. The ladder gives us the first honest answer. At 0.1 c, the mission is thousands of years. At 0.01 c, it is centuries. At 0.1, it is decades. Decades are the first rung that resembles a human project, and that rung already demands technology beyond our current reach. It also demands a social commitment to continuity, because the mission must outlast political cycles and economic fashions. Relativity does not soften that conclusion at these speeds. Time dilation is measurable, but it is not transformative until you are near light speed. The cinematic shortcut, arrive young after a long trip, requires velocities that are almost unimaginably expensive. Communication delay does not soften it either. Even success means living with years of silence between question and answer. What does leadership look like when guidance arrives after the crisis is over? Navigation does not soften it. The longer the path, the more precision becomes survival, and the more correction becomes cost. The ship must be both an observatory and a workshop, because it cannot outsource competence to Earth. Distance is the universe's first no because it multiplies everything that follows. It multiplies energy requirements, shielding demands, and the probability of failure. It also multiplies the weight of every decision made before launch, and distance is only the first wall. Next comes the price of speed, where the math stops being inconvenient and starts being punishing. The moment you demand decades instead of centuries, you step into a different category of physics. We have been promised the stars for a century, and the promise survives by skipping this ladder. When we climb it carefully, the dream does not die, but it changes. It becomes more precise, more demanding, and more honest. It becomes less like a weekend trip, and more like a civilization choosing what it is willing to pay and what it is willing to become. The question is not whether the stars are there, but whether we can endure what it takes to reach them. In the next chapter, we price the velocity itself. We ask what energy and propulsion must look like to climb from decades toward years. Distance set the scale. Now we price the act of changing that scale with speed. Interstellar travel is a velocity problem first, because time is distance divided by speed, and human patience is a hard boundary. But the moment you demand higher speed, distance returns as a multiplier. More distance means more time exposed to failure, and more speed means more energy you must buy. In space, there is no road to grip and no air to push against, so momentum is the currency. If you want to change your momentum, you must throw something the other way, and you must do it with discipline. That simple fact, Newton's third law, spoken in plain language, becomes the oldest tax in astronautics. Engineers compress this entire argument into one line of math. It is called Tsiolkovsky's rocket equation, and it is the cleanest cruelty in spaceflight. It does not care about optimism, only about momentum, mass, and the unforgiving arithmetic of exponentials. Konstantin Tsiolkovsky wrote it down in the early 20th century, long before liquid rockets proved him right. He was thinking about spaceflight as a physical inevitability, not a fantasy, yet his equation reads like a warning label. A century later, every launch vehicle, from a small satellite booster to a heavy lift rocket, still bows to the same line. The equation links three ideas. Delta V is the total change in velocity your mission can produce, summed across everything you do. Exhaust velocity is how fast your engine throws propellant backward, measured relative to the vehicle. Mass ratio is how much heavier you start compared to how much you end after you've spent propellant. Delta V is not your top speed, and it is not a single burn captured in a dramatic shot. Delta V is your budget for every major maneuver, including the ones you hope you never need. You spend it on leaving Earth, shaping a trajectory, correcting errors, avoiding hazards, and arriving with control rather than desperation. In mission design, Delta V is treated like money with interest and penalties. You allocate it to planned burns, then you add margin, because sensors drift, engines underperform, and the universe does not sign contracts. That margin is not a rounding error for interstellar missions. It becomes a structural feature of the vehicle. For interstellar missions, Delta V becomes the mission's core currency. If you want to cruise at 0.1 c, you must accelerate to that speed, not just point yourself and hope. If you want to do more than a flyby, you must also decelerate by roughly the same amount so you can stay. That is the first brutal simplification. A meaningful visit usually needs two big velocity changes, one to speed up and one to slow down, so the Delta V requirement is often close to twice the cruise speed, before you count course corrections, reserves, and the messy reality of navigation. It also means the ship must be built for two different moments of violence. One is departure, when the vehicle is heaviest and every system is new. The other is arrival, when the vehicle is lighter but older, and the crew is tired and the target star is still moving. Exhaust velocity is the lever you get from your engine. If you can throw propellant out faster, each kilogram of propellant buys more Delta V, which is the whole game. In rocketry language, higher exhaust velocity means higher specific impulse and better leverage against the equation's trap. Specific impulse is often described in seconds, which sounds abstract until you translate it back into exhaust speed. Those seconds are a measure of how efficiently an engine turns propellant into momentum, how hard it can push for a given flow. In deep space, that efficiency becomes the difference between a ship and a fuel tank with a name. Mass ratio is the price you pay for that leverage. It is initial mass divided by final mass, including everything you keep after the burn. Final mass includes payload, structure, tanks, engines, shielding, avionics, and whatever propellant remains for later, because later always arrives. The rocket equation says delta V equals exhaust velocity times the natural log of mass ratio. The log is the trap, because it grows slowly even as mass ratio grows wildly. It means gains in delta V require exponential growth in propellant, unless exhaust velocity rises dramatically. Here is the intuition without the symbols. A rocket is a vehicle that must carry its own reaction mass, and it must carry it from the start. Every kilogram of fuel you add is also a kilogram you must accelerate, and that acceleration itself needs more fuel. It is like dragging your own gas station across a desert. The more fuel you bring, the heavier the gas station becomes and the more your tyres sink. The heavier it becomes, the more fuel you must bring to move it, and the spiral tightens. In visuals, you can almost see the loop. A tank grows, then the engine grows to push the tank, then the tank grows again to feed the engine. The payload, what you actually care about, shrinks toward a bright stubborn dot. This compounding is not a design flaw. It is conservation of momentum written in engineering form, and it is as old as physics. Rockets work by throwing mass away, and the cost of throwing mass away is that you had to carry it first. At low delta V, the spiral is manageable, and the equation feels like a constraint rather than a prison. That is why chemical rockets can reach orbit and send probes to planets with elegant trajectories. But as delta V climbs, the spiral tightens until it dominates everything else you care about, including safety. A chemical rocket has an exhaust velocity around 4.5 kilometers per second, give or take. That number is set by chemical bond energy and nozzle physics, and it does not scale to interstellar needs. It is excellent for leaving Earth, and almost irrelevant for reaching another star quickly. To see why, do a simple comparison that fits on a screen. Interstellar cruise speeds are often discussed in thousands to tens of thousands of kilometers per second. Chemical exhaust is a few kilometers per second, which means the rocket must be mostly propellant to reach even modest fractions of c. The equation does not forbid it in principle. It just demands mass ratios that become absurd in practice, pushing past what you can build, launch, or even assemble. The vehicle becomes a propellant container with a tiny payload, and then a propellant container for the propellant container. Even before Interstellar, this is visible in real launch vehicles on the pad. Most of the mass is propellant, and most of what reaches orbit is not payload, but empty tanks and engines that did their job. The rocket equation is why staging exists, and why rockets look like stacked cylinders of metal. Staging is a partial escape because it lets you drop empty structure at the moment it becomes dead weight. You reset the mass ratio by discarding tanks, plumbing and engines, then light a smaller rocket that begins with a fresh advantage. But staging adds complexity, failure points, and more structure that must be carried early. For interstellar missions, staging becomes a whole architecture rather than a single event. You might stage in Earth orbit, then stage again after leaving the solar system, and perhaps again during cruise. Each stage must be built, fueled, chilled, and ignited reliably, far from repair and far from rescue. The deeper problem is that interstellar travel does not ask for one big burn. It asks for a long chain of burns, corrections, and contingencies, because the target is distant and the timeline is long. Each contingency reserve increases starting mass, which increases propellant, which increases starting mass again. Now add the payload reality that science fiction often hides behind a sleek hull. Humans require habitats, life support, food systems, radiation shielding, medical capacity and redundancy that can survive years of isolation. Those are not optional accessories. They are the mission, because without them, the ship is only a fast coffin. Radiation shielding is heavy, and micrometeoroid protection is heavy, and both are dictated by the environment rather than taste. In interplanetary space, cosmic rays and solar storms already matter, and in interstellar space the exposure time stretches. At high speed, even sparse dust becomes a hazard, which pushes you toward thicker shielding. The danger is not dramatic like a movie explosion, it is granular and relentless. A grain of dust at a significant fraction of c carries kinetic energy that behaves like a tiny bullet, and shielding must spread that energy out. Thicker shielding increases mass, and the rocket equation punishes that mass twice, once in acceleration and again in braking. Structure is also mass, and structure grows with propellant load in a quiet but decisive way. Bigger tanks need stronger walls, and stronger walls add more mass, and that mass must be supported through thrust loads and thermal cycling. That extra structural mass then requires extra propellant to accelerate it, which grows the tanks again. Life support is not just oxygen and water. It is pumps, filters, valves, sensors, microbial control, spares, and the ability to survive failures for years without a supply chain. Every spare part is mass, and every kilogram of spares is another kilogram the rocket equation makes you pay for. Even the invisible systems have weight. Power conditioning, wiring harnesses, computers, attitude control and communication hardware all accumulate, and they must be hardened against radiation. When the timeline is measured in years, reliability becomes a form of mass, because redundancy is the simplest way to buy it. So interstellar travel becomes a coupled problem, not a single engineering challenge. The more you plan for safety, the heavier you get, and the heavier you get, the more propellant you need. The more propellant you need, the more structure you need to hold it, and the loop closes again. This is why interstellar travel is not only a distance problem, it is a velocity problem that drags distance back into the room, because long distances force high speeds for human timelines. High speeds force mass ratios that explode, and exploding mass ratios force designs that stop being ships and become infrastructure. To keep the story honest, we should name what the equation is not saying. It is not saying rockets cannot work in space, and it is not saying progress is impossible. It is saying that propulsion improvements must be dramatic, not incremental, because the log punishes small gains. So we compare propulsion families by their exhaust velocity, because that is the lever in the equation. Chemical propulsion sits at the bottom of the ladder, with exhaust around 4.5 kilometers per second. It is mature, powerful, and fundamentally limited by chemical bond energy, which is small compared to nuclear scales. Nuclear thermal propulsion moves the lever upward. A nuclear reactor heats hydrogen and throws it out a nozzle, reaching roughly 8 to 9 kilometers per second exhaust in many studies. That is about double chemical, which is a real improvement for deep space missions where every percent matters. Historically, nuclear thermal was not just a thought experiment. In the mid-20th century, test programs fired reactor engines on the ground, proving that the basic physics works. Yet the practical barriers, politics, safety, cost and materials, kept it from becoming routine, even before we asked it to chase stars. But doubling exhaust velocity does not double your reach. The log in the equation means you still hit exponential walls at high delta V, and those walls arrive sooner than intuition expects. Nuclear thermal helps for fast trips within the solar system, and does not make 0.1c missions reasonable for human-scale payloads. Electric propulsion, like ion engines, changes the trade. Ion exhaust velocities can reach tens of kilometers per second, sometimes higher, because electricity can accelerate ions far beyond chemical flame temperatures. That is an order of magnitude above chemical, which sounds like the breakthrough we need. The catch is thrust, and thrust is what the camera feels. Ion engines push gently, because they are limited by power and by how much propellant they can ionize and accelerate per second. They can accelerate for months or years, but they cannot shove a heavy crewed ship quickly without enormous electrical generation. For interstellar travel, low thrust is not just inconvenient. It changes mission geometry, because you spend long periods accelerating, and those periods stretch your exposure to radiation and micrometeoroids. That can be fine for robotic probes, but human missions often need tighter schedules and stronger control authority. Electric propulsion also forces another accounting system. If you want high exhaust velocity, you must supply energy to accelerate the propellant, and that energy must come from somewhere. Power systems bring mass, radiators bring area, and both must survive for years, which the rocket equation then punishes again. In other words, better exhaust velocity is not free. It often arrives with heavier power hardware, and heavier hardware increases the mass ratio you need, even if you save propellant. The equation does not care whether mass is fuel or reactor. It only cares that you must accelerate it. Then we reach the conceptual tier that interstellar dreams lean on. Fusion propulsion is often described with exhaust velocities in the hundreds to thousands of kilometers per second, depending on the design and how much reaction mass you carry. In principle, that is the kind of number that begins to match interstellar cruise speeds. If you could throw reaction mass out at 1,000 kilometers per second, the mass ratio for a given delta V becomes less insane. You still need propellant, but you need far less of it, and the ship can begin to look like a mission rather than a fuel depot. The rocket equation loosens its grip, though it never lets go. But fusion is not a single technology. It is a family of extremely hard problems, including confinement, ignition, materials erosion, neutron damage, and waste heat that must be rejected into space. A fusion rocket must be a power plant and an engine, operating reliably for years with no maintenance bay. Even if fusion works, you still face the two-burn reality. You must accelerate, then decelerate, unless you accept a flyby and call it a visit. Deceleration is not an afterthought. It is half the delta V bill, and it arrives when your options are narrow. This is where mission architecture becomes the story. If you carry propellant for braking, you must also accelerate that braking propellant during departure, which which is the cruel recursion. That increases departure propellant, which increases structure, which increases departure propellant again, until the design becomes dominated by what it must carry for later. Some proposals try to break the loop by moving propellant off the ship. You can imagine beamed energy pushing a light sail, or a magnetic sail breaking against the interstellar medium, or other externalized momentum exchanges. These ideas shift mass off the vehicle, but they shift difficulty onto infrastructure, pointing accuracy and control. A beamed sail needs a transmitter of staggering power and precision, held stable for years as the target recedes into darkness. It also needs a sail that survives acceleration, micrometeoroids, and heating without tearing or warping. The rocket equation relaxes, but the energy and engineering demands move elsewhere. A magnetic sail or electric sail can, in theory, break without carrying propellant, using large electromagnetic fields to interact with sparse particles. But the interstellar medium is extremely thin, so the braking force is weak, and weak braking means long braking distances. That pushes you to start slowing far from the target, long before the destination looks real. So the rocket equation is not the only tyrant, but it is the first one you can write down. It turns every wish into a mass ratio, and every mass ratio into a design that must exist in metal. It forces you to ask what you are actually launching, and what you're willing to leave behind. Now we connect back to the central question. Are we physically capable of sending humans to another star within a meaningful timescale, rather than a mythic one? The rocket equation does not answer yes or no, but it narrows the path sharply until only a few propulsion regimes remain plausible. If you insist on chemical propulsion, meaningful timescales collapse into fantasy, because the mass ratios become unlaunchable and unbuildable. If you move to nuclear thermal, you gain capability inside the solar system, not a human interstellar ship. If you move to electric propulsion, you gain exhaust velocity but trade for power and time. Fusion, antimatter catalysis, or other high-energy concepts might raise exhaust velocity enough to make the mass ratios survivable. But survivable mass ratios are not the same as a survivable mission, because mass is only one axis of risk. You still must protect humans, sustain life, and arrive with control, not just arrive. The equation also explains why interstellar mission studies keep shrinking payloads, often down to gram-scale probes. A gram-scale probe can tolerate tiny shielding, minimal redundancy, and a short operational life at the target. A human habitat cannot, and the mass penalty is not linear, it is multiplicative. So the rocket equation becomes a filter on dreams. It rewards small, fast unmanned craft first, because they can accept fragility and still succeed. It punishes large, crude ships until propulsion and energy reach a different regime, where exhaust velocity and power density change by orders of magnitude. This is the tyranny in a single line. It is not a ban, it is a demand for extreme performance, and it is brutally specific about what extreme means. It says that interstellar travel is not one invention away, because the invention must shift the mass and energy scales by orders of magnitude. Staging can help, and it will almost certainly be required, because discarding dead mass is one of the few tricks we have. But staging also multiplies operations, assembly and failure modes, and it stretches the chain of things that must go right. A multi-stage interstellar vehicle is not a rocket. It is an industrial project launched into deep time, and every added system has a shadow cost. Tanks require insulation and plumbing requires valves, sensors and heaters to prevent freezing or boiling. Reactors require shielding and radiators require area and micrometeoroid protection. Protection requires more mass, and mass restarts the loop. So we end with a sober transition. Even if an engine exists on paper, the mission still has to pay for the energy. The rocket equation tells you how much propellant you need, and energy physics tells you how much power that propellant represents. In the next chapter, we follow that bill into its second ledger. We ask what it means to accelerate a human ship to interstellar speed, then remove that energy again to stop. Distance set the scale, and the rocket equation set the mass trap. Now we translate propulsion into its other language: energy, power, and the size of the bill. The key idea is simple and merciless, and it hides in a familiar equation. Kinetic energy rises with velocity squared, so speed is not a dial, it is a multiplier. On screen, the curve looks polite at first. Then it bends upward like a cliff. Double the speed and the energy quadruples. Triple the speed and the energy becomes 9 times larger before we add any real-world inefficiency. That squared law is why interstellar timelines keep steering us toward point 1c. That is about 30,000 kilometers per second, fast enough to make decades into years, and expensive enough to make nations blink. Start with a payload that sounds modest by human standards, not by rocket standards. Imagine 100 metric tons for habitat, shielding, systems, and a small crew. Picture it in a hangar, a compact cylinder of pressure hull, water tanks, radiation shelters, and redundancy stacked like a submarine. Even before propulsion, it is already a miniature world with life support, spares, and failure tolerance. At point 1c, the classical kinetic energy is 1/2 mv squared, and the numbers stop feeling like engineering. For 100,000 kilograms at 30 million meters per second, the result is about 4.5 times 10 to the 19 joules. Write that number down and sit with it, because it is not fuel yet. It is the energy stored in the ship's motion. Energy that must be purchased, converted, and delivered without melting your own machinery. It helps to translate joules into something physical, even if the comparison is imperfect. That energy is comparable to many billions of tons of chemical explosive, compressed into a single moving object. Now remember the earlier warning about arrival, because the universe charges twice. If you want to stop, you must remove almost the same energy again, and braking is not optional for a meaningful mission. A flyby is a postcard at relativistic speed, a blur of photons and missed opportunities. A crewed mission needs time to observe, to maneuver, and to survive in a new star system. So the trip's minimum energy ledger is roughly doubled. For 100 tons to 0.1 c and back to 0, you're near 9 times 10 to the 19 joules, before margins. But even this staggering number is a lie, a comforting underestimate. Because everything we've calculated so far assumes a perfect universe. No mistakes, no course corrections, no failures, nothing going wrong across decades of travel through the void. And deep space does not do perfect. The real energy bill is higher, and later in this video we'll show you just how much higher, and why this single overlooked factor may be the thing that keeps us trapped in our own solar system forever. For now, start with the first hidden cost. Margins are not a luxury in deep time because deep time multiplies small errors. Course corrections, reserves, and failures add energy demand, and each added kilogram raises the bill again. Even navigation has a price tag because momentum is stubborn. Over years, tiny thrusts become necessary to trim trajectories, avoid hazards, and keep antennas pointed home, each correction paid for in reaction mass or power. Translate that number into something a civilization recognizes, and the scale snaps into focus. World energy use is on the order of 10 to the 20 joules per year, so a 100-ton mission to 0.1 c, with braking, sits near a year of total human energy consumption. That is for one ship, not a fleet. And that comparison is generous because it assumes a magical accounting trick. It assumes perfect conversion of stored energy into directed kinetic energy, with no waste heat and no losses. Real engines spill entropy everywhere, and thermodynamics keeps the receipt. Every conversion step, reactor to electricity, electricity to beam, beam to thrust, bleeds energy into heat that must go somewhere. Real power systems are also not massless, and mass is destiny in spaceflight. Tanks, turbines, coils, radiators, and shielding all add kilograms, and kilograms demand more energy to accelerate and brake. If your overall efficiency is 10%, the primary energy requirement grows by 10. Then the mission stops looking like a big project. It starts looking like a global energy program dedicated to a single departure. This is where the story turns from fuel tanks to infrastructure, and the visuals widen. The question becomes whether we can concentrate energy at the needed rate, not just the needed total. Energy is a total, but power is a schedule, and schedules decide engineering. A ship that accelerates in 1 year needs far more power than a ship that accelerates in 20. At 0.1 c, even gentle acceleration implies extreme power, because the energy is so large. If you spread 4.5 times 10 to the 19 joules over 1 year, you need roughly 1.4 terawatts. That is comparable to the average power of a major industrial nation, delivered continuously and reliably, and that is only for the acceleration phase of 100-ton payload. Now imagine the supporting hardware in motion, glowing radiator wings, humming power buses, and a thrust plume that must remain stable for months. In deep space, there is no maintenance dock, only what you brought. If you demand faster acceleration for crew comfort or mission design, the power scales upward again. The energy bill stays, but the power plant must grow. Crew comfort sounds soft, but it becomes hard physics when you count time under thrust. Higher acceleration can shorten exposure to cosmic rays and reduce mission duration, yet it also demands heavier systems and harsher thermal loads. The squared law is only the opening act, and it is still Newton speaking. As speed rises further, relativity steepens the curve, and the universe charges extra for approaching its limit. We can explain this without heavy math, because the intuition is enough. Classical kinetic energy assumes mass is constant, but relativity treats energy and momentum as linked more tightly at high speed. At low fractions of c, the correction is small, and the old equations are honest. At higher fractions, each additional increment of speed costs more energy than the last. At 0.1 c, the relativistic correction is minor, and Newton still mostly works. That is why 0.1 c is a common target in serious studies, including early fusion rocket papers and modern sail concepts. But the temptation is to keep turning the speed dial, because time is the most seductive metric. If you chase 0.3 c or 0.5 c, time improves, yet energy demand grows faster than v squared. Near light speed, energy climbs toward infinity in the idealized limit, and the curve becomes a wall. The universe does not forbid the approach, but it makes it financially absurd. Relativity also punishes you operationally, and the punishment has teeth. Higher gamma means higher radiation intensity in the ship's frame, and higher energy for every dust grain you hit. A grain of interstellar dust is tiny, but at 1/10 the speed of light it becomes a projectile with the energy of a bullet. At higher fractions of c, it becomes something closer to a microscopic bomb, hard to detect, harder to stop. So energy is not just a launch problem, it is a design problem that spreads everywhere. Energy is also a shielding problem, a reliability problem, and a safety problem that scales with speed. This is the energy reality check, and it arrives before any argument about engines. Even before we choose a propulsion method, the kinetic energy of a useful payload at 0.1 c is already enormous. Now we ask the question that always follows, because engineering begins with budgets. What energy source could plausibly pay this bill, with the power density and mass constraints a ship demands? Chemical fuel is eliminated immediately, not by pessimism but by arithmetic. Chemical bonds cannot supply enough energy per kilogram to push a large payload to 0.1 c, especially with braking. Even the best chemical propellants release energy on the order of tens of megajoules per kilogram, and most of that becomes hot exhaust. Interstellar kinetic energy demands many orders of magnitude more, so many that clever staging cannot rescue it. Nuclear fission has far higher energy density than chemistry, and it has decades of operational history. But fission reactors are heavy, and their power output is limited by heat rejection and materials. A reactor is not just a core, it is pumps, shielding, control systems, and radiators that must glow in the cold. In space, every watt of waste heat must be radiated away, and radiators grow like sails made of metal. Fission can support high-power electric propulsion for solar system missions, where megawatts matter and travel times are flexible. It does not obviously scale to terawatt-class propulsion for a crewed interstellar ship. So the conversation jumps to fusion, and the tone changes because fusion feels like destiny. Fusion is often treated like a magic word, because stars run on it, and equations promise huge energy per mass. Historically, that promise has been with us since the mid-20th century, when scientists first mapped stellar fusion pathways and imagined engines to match. The dream has persisted through changing designs, magnetic bottles, inertial pellets, and pulsed micro-explosions, because the prize is so large. Fusion in a lab is not fusion as a rocket, and that distinction is where reality lives. A lab demonstration can be brief, delicate, and supported by a planet's worth of infrastructure. A fusion rocket must be compact, robust, and restartable, and it must behave like a machine. It must run for months or years with predictable thrust, in a radiation environment of its own making. It must also carry reaction mass, because energy alone does not move you in a useful direction. Fusion releases energy, but rockets need momentum exchange, and momentum still requires throwing mass out the back. This is where hype often hides a missing term, and the missing term is propellant. Even with fusion, you do not get to accelerate without propellant, unless you use an external push. If your exhaust is fusion products alone, thrust is limited by how much fusion you can sustain and by how well you can direct the exhaust. If you add extra propellant to raise thrust, you dilute performance. High specific impulse is not the same as high thrust, and the difference matters for cruise. A fusion system might offer great exhaust velocity, yet still struggle to push a heavy crewed ship quickly. Then there is the waste heat problem, which is the quiet dictator of spacecraft design. Any realistic fusion engine produces heat that must be radiated away, and radiators grow with power. Radiators are not just panels, and the visuals should linger on them. They are mass, area, and vulnerability, and they must survive impacts and degradation for decades. Fusion also has a materials problem, and it is not a footnote. Many fusion reactions produce neutrons that damage structures, embrittle metals, and activate components into radioactive waste. A terrestrial reactor can replace parts and accept downtime because it sits inside a supply chain. An interstellar ship cannot, and it must carry spares that the rocket equation punishes. So fusion is not dismissed, but it is not a free pass. It is a research frontier that must become an industrial engine, not a physics experiment. If fusion is the optimistic option, antimatter is the extreme one, and it feels almost mythic. Matter-antimatter annihilation offers the highest energy density allowed by known physics. In principle, antimatter could shrink the fuel mass dramatically, because mass converts directly into energy. In practice, the production scale is the first wall, and it is nearly vertical. We can make antimatter today, but only in tiny quantities, in particle accelerators built for science. The energy cost to produce it is enormous, and the efficiency is poor. To fuel an interstellar mission, you would need grams to tons depending on design, and the range is still terrifying. Humanity has produced far less than a microgram in total. Even if you could afford the energy to make it, you must store it, and storage is not passive. Antimatter cannot touch normal matter, so containment must be perfect. Magnetic traps can hold charged antiparticles, but only in small numbers and at extreme vacuum, with careful field geometry. Neutral antimatter, like antihydrogen, is even harder to confine because it does not respond as strongly to electromagnetic control. Storage is not just a container, it is an active system that must never blink. It needs power, cryogenics, control fields, and fault tolerance for years. Any containment failure is not a leak, it is an explosion, and the scale is unforgiving. Even small losses become catastrophic when the fuel is pure annihilation energy. There is also the exhaust problem again, because rockets need directed momentum, not raw brightness. Annihilation produces high-energy gamma rays and particle showers, which are hard to collimate into thrust. If you cannot direct the energy, you get heat and radiation instead of momentum, and then you pay twice. Then you need shielding and radiators, and the mass advantage erodes. So antimatter is unmatched in theory and blocked in practice, like a sign at the edge of the map. It is not a near-term fuel, it is a boundary marker for what physics allows. If onboard fuel is the trap, we try moving the power plant off the ship and the camera pulls back to the home system. Beamed propulsion proposes exactly that. Push the craft with energy sent from home. Laser sails and microwave sails replace onboard engines with a large sail, thin as foil and wide as a city. The sail intercepts a beam, and the beam's momentum provides thrust. This shifts the rocket equation, and that shift is profound. The craft can be lighter because it carries less propellant, and lighter craft are easier to accelerate. But the energy problem does not vanish. It relocates to the transmitter, and relocation has its own price. The transmitter must deliver enormous power with extreme precision over vast distances. A sail accelerated to 0.1 c needs sustained beam power, and the beam must stay locked as the craft recedes. If the sail is light enough, the required power can be within plausible future megastructure ranges. The infrastructure is still gigantic, and it is not just one device. You need an array kilometers to thousands of kilometers across, depending on wavelength, to keep the beam tight. Diffraction is the quiet enemy, written into wave physics. Beams spread with distance, so the farther the sail goes, the harder it is to keep pushing effectively. That means the hardest part is early acceleration, when the beam is intense and the sail is still close enough to ride it. You must dump huge energy into the sail while it is still near home, and the thermal margins are razor thin. Beam control is also navigation control, and the coupling is intimate. Any pointing error becomes a miss. and any miss becomes wasted energy that does not come back. The sail itself is a materials challenge, and it must be more than light and shiny. It must be ultralight, highly reflective, and able to survive heating, micrometeoroids, and acceleration stress. For microwave sails, the sail can be larger and more tolerant, because the wavelength is longer and the beam can be gentler, but the transmitter must be even larger and the power system must still be immense. Beamed propulsion also raises a strategic question, and it arrives whether we want it or not. A multi-terawatt beam is not just a space project, it resembles a weapon in capability. So the governance problem appears, and it is as real as the optics. Building the infrastructure requires global coordination, long-term stability, and trust that the beam stays on mission. Beam propulsion also does not solve arrival by itself, and the story loops back to the same wall. You can push easily from home, but you still must slow down at the destination. You can imagine a second beam station waiting at the target star, built by earlier probes or autonomous factories. But that requires pre-positioned infrastructure, which is its own interstellar mission. You can imagine braking with a magnetic sail against the interstellar medium, letting fields bite into sparse plasma, but the medium is thin, so braking distances become enormous. You can imagine braking against the destination star's light with a photon sail, using starlight as a natural beam. That can help, but it is limited, and it constrains approach geometry. So beaming shifts the burden rather than erasing it, and the trade is stark. It trades onboard propellant for offboard power and precision, and it replaces one impossibility with another kind. Across all these concepts, the theme is consistent, and it is worth stating plainly. Interstellar speed is not mainly an engineering detail, it is an energy economy problem. The universe is not asking for cleverness alone, it is asking for commitment at scale. It is asking for sustained, concentrated power at levels we usually reserve for civilization maintenance. That observation is both sobering and inspiring, because it reframes what a starship really is. A starship is not only a vehicle, at these speeds it is a policy, an industry, and a long-term allocation of planetary effort. This reframes the central question, and it sharpens the awe rather than diminishing it. Are we physically capable of sending humans to another star on meaningful timescales, or are we narrating a belief? Physics does not say no, and it does not say yes with a smile. Physics says pay in energy, pay in infrastructure, pay in reliability, and pay again to stop. Now we tighten the story toward the next limit, because limits come in layers. Suppose we somehow pay the energy bill, and we build an engine or a beam that works. We still have to arrive, and arrival is where the numbers become personal. Arriving at 0.1 C is not arrival, it is impact unless you can shed that kinetic energy safely. In the forward view, the destination star grows from a bright point to a hard sun, while the ship carries a nation's energy in its motion. What does it mean to approach a new world as a relativistic meteor, when the act of stopping is as demanding as the act of leaving? So the next chapter turns the ship around in our minds, and it holds the camera on the braking problem. We ask how to brake in interstellar space, without carrying an impossible second ship of fuel. The promise of the stars survives by skipping the bill and skipping the stop, and that is the temptation. Honest awe begins when we keep both in the frame. Suppose we somehow pay the energy bill and we build an engine or beam that works. The optimistic timeline still hides a second demand. You must arrive with control, not just arrive. In every spaceflight story we tell ourselves, arrival feels like a finish line. Yet in physics, arrival is a negotiation. The destination is not waiting in your frame. It is moving around its star, and the star is moving through the galaxy. Interstellar travel is not one velocity change. It is two major velocity changes separated by years of exposure. Acceleration is only half the mission. Matching velocity with the destination is the other half. Delta V is not a bragging number, it is a full mission budget. It is the ledger entry that connects your propulsion choice to everything else you must carry. When mission planners talk about Delta V, they are really talking about options, margins, and failure modes. If you cruise at 0.1 C, you must gain about 0.1 C. If you want to stop, you must lose about 0.1 C again. Even before you add course corrections, plane changes, and contingencies, the symmetry is already waiting. That simple symmetry doubles the requirement before corrections and reserves. It also doubles the energy you must manage, because kinetic energy is still sitting in your motion. The ship becomes a moving storage device for a civilization-scale investment. At relativistic fractions, the bookkeeping gets sharper, not softer. Kinetic energy rises faster than speed, and momentum becomes stubborn. Even at 0.1 C, you are carrying an energy scale that makes ordinary engineering feel small. This is the deceleration paradox. The faster you go to make the trip shorter, the harder it becomes to make the trip end. You can cross the distance and still fail the mission at the last moment. Visually, it is like throwing a needle across a room and demanding it stop inside a thimble. The room is the interstellar gulf, and the thimble is a stable orbit. The throw is easy to imagine, but the catch is where reality collects its price. The difference between a flyby and a rendezvous is the difference between a glance and a presence. A flyby accepts that the target system is a blur. A rendezvous demands that the ship becomes part of that system's clock. That clock is literal. Planets have orbital velocities of tens of kilometers per second. Moons add their own motion, and the star's gravity reshapes trajectories. If you do not match the local frame, you are not visiting a place. You are slicing through it. At 0.1 C, the closing speed is about 30,000 kilometers per second. Even the outer regions of a star system are crossed quickly at that rate. The useful window can shrink to minutes or hours. Picture the scene from the probe's perspective. A distant star swells from a bright point to a glaring disk, while the sky fills with unfamiliar constellations. Then the planets appear, tiny beads that grow too fast, turning into streaks before your instruments can blink. A fast probe can still do science, but it must be designed for a sprint. Instruments must capture data instantly, compress it, and transmit it with little chance for retakes. Navigation and pointing must be pre-planned with ruthless precision. That means sensors with high dynamic range, shutters that can survive intense glare, and processors that can decide what matters in real time. It also means timing that is almost musical, each observation triggered by predicted geometry, because there is no time to improvise. Even communication becomes part of the sprint. The probe must store bursts of data, then beam them home across light years with limited power. Every bit sent is a choice, and every missed target is permanent. For humans, a flyby is not a visit. You cannot explore, repair, or improvise while everything outside is rushing past. You cannot build a settlement while your trajectory is a bullet. Human missions also carry psychological and operational needs that physics does not forgive. You need time to survey hazards, time to choose landing sites, and time to respond to surprises. A flyby offers none of that, only spectacle and loss. So the mission architecture splits into two categories. Flyby missions trade control for feasibility. Settlement and exploration missions demand braking, and braking demands momentum exchange. Momentum exchange is the core word, because it tells you what must happen. You're moving fast, and you must give that motion to something else. If you cannot hand it off, you keep it, no matter how beautiful the destination looks. The first braking option is the most intuitive. Carry propellant and fire an engine to slow down. It sounds like the clean solution, until the rocket equation returns with compound interest. The rocket equation is not a mere formula, it is a structural constraint. It says that to change your velocity, you must throw mass away at high exhaust speed. When the required delta V is enormous, the required mass ratio becomes the mission. Braking propellant is not just carried, it must be accelerated during departure, which increases departure propellant, which increases structure, which increases departure propellant again. The recursion is the design. This is why staging appears in every serious rocket history. From early multi-stage launches to deep space probes, engineers learned that carrying your own braking mass is brutally expensive. Interstellar scales do not erase that lesson, they amplify it. If your engine has high exhaust velocity, the mass ratio pain is reduced but not erased. If your engine has low exhaust velocity, the mass ratio becomes a disaster quickly. For crewed payloads, the penalty stacks on top of shielding and redundancy. High exhaust velocity usually implies high energy per kilogram of propellant. That pushes you toward fusion, antimatter catalysis, or other extreme concepts, each with its own engineering cliffs. Low exhaust velocity pushes you toward carrying oceans of reaction mass, which becomes its own impossible ship. Even with advanced propulsion, braking is often as hard as accelerating. You need comparable delta V, comparable thrust control, and comparable reliability after decades of wear. Arrival is not a victory lap. It is another launch, performed far from help. Think about what reliability after decades really means. Valves must still seal, power electronics must still switch, and sensors must still calibrate. A single stuck actuator at arrival can turn a planned orbit into a fatal hyperbolic escape. A second idea borrows from planetary missions. Use an atmosphere to brake, turning speed into heat. It works at Mars and Venus, and it looks like a free gift. Historically, aerobraking became a quiet triumph of robotic exploration. Spacecraft dipped into thin air again and again, using drag as a substitute for propellant. It was elegant, until you imagine doing it at interstellar velocities. Interstellar arrival rarely offers that gift when you need it. There is no thick atmosphere in deep interstellar approach. Even if a planet exists, you do not want to hit its air at relativistic speed. At high fractions of C, aerobraking becomes closer to ablation than braking. Heating rates become extreme, and shock physics becomes violent. A small guidance error becomes catastrophic, because the corridor for survival is narrow. The air in front of you does not merely warm, it ionizes into plasma, radiates intensely, and can strip material from your shield faster than you can imagine. The difference between slow down and disintegrate becomes a matter of meters and milliseconds. You could try to break in the upper fringes of a gas giant or skim a star's outer atmosphere, but the required precision is brutal, and the environment is not gentle. Radiation, turbulence, and debris turn the maneuver into a gamble. A star's outer layers are not a calm surface, they are a boiling boundary. Magnetic loops and convection cells can be larger than planets, and charged particles can hammer exposed systems. Skimming that boundary at high speed is like threading a needle through a storm. A third family of ideas avoids carrying propellant. Use a sail that interacts with the medium between stars. The ship trades momentum with what it passes through, instead of with fuel it brought. This idea echoes older dreams of sailing ships and trade winds, translated into plasma and fields. It is appealing because it turns the universe into your reaction mass. Yet the universe, between stars, is thin, so thin that wind becomes a metaphor. A magnetic sail is the flagship concept in this category. It deploys a large loop or field structure that deflects charged particles. The deflection transfers momentum to the ship, producing drag without propellant. In visuals, imagine a ghostly bubble around the craft, an invisible magnetic umbrella spanning kilometers, maybe more. Incoming ions spiral along field lines, curve away, and in that curvature the ship feels a gentle, persistent push backward. The promise is elegant, because it externalizes the reaction mass. The trap is density. The interstellar medium is extremely thin, and thin medium means weak braking force. Typical interstellar particle densities can be only a few atoms per cubic centimeter, sometimes less. That is emptier than the best vacuum chambers on Earth, and it means your sail is grabbing at almost nothing. Even a huge magnetic cross-section can yield only a faint deceleration. Weak force means long braking distance. You must start slowing far from the destination, sometimes years before arrival. That stretches mission time, increases exposure, and demands that the sail survive for decades. Long braking arcs also change the story's pacing. The craft begins its arrival while the star is still a bright dot, and the mission enters a slow, patient phase. It is less like slamming on brakes, and more like easing a freight train to a stop. Magnetic sails also depend on plasma behavior that is hard to predict remotely. The local ion density, temperature, and magnetic field shape the interaction. Small modelling errors can produce large performance errors over long distances. Plasma is not a simple gas. It carries currents, generates instabilities, and can reconnect magnetic field lines in sudden events. A sail that looks stable in a simulation may flutter, oscillate, or lose efficiency in a real turbulent medium. An electric sail offers a related approach. It uses charged tethers to repel ions in the solar wind or interstellar plasma. It can be lighter than a magnetic loop, but it still depends on the same sparse particle environment. Those tethers would be long, thin, and delicate, threads stretched into darkness. They must hold charge, resist micrometeoroid cuts, and remain deployed without tangling. The engineering is not impossible. but it is unforgiving. Both sail types face a control problem. Large electromagnetic structures must remain stable and oriented. They must survive impacts, charging events, and gradual degradation while providing consistent drag. Control is not just attitude control, it is survival control. If the sail twists, it can change your deceleration vector, which changes your aim point years later. A tiny angular error early can become a planetary miss at the end. A fourth option uses photons instead of particles. A sail can break by reflecting light, stealing momentum from a beam or from starlight. In principle, photon momentum is always available, because stars shine. The physics is simple, even if the engineering is not. Light carries momentum and reflection doubles the push. A bright star is a fountain of photons and a sail is a mirror trying to catch them. In practice, photon braking is weak unless the sail is enormous. Starlight pressure falls with distance squared, so it is feeble far from the star. To get meaningful deceleration, you need huge area, low mass, and careful approach geometry. That geometry shapes the visuals of arrival. The craft does not dive straight toward its target planet. It may swing inward toward the star first, presenting its sail like a shield, trading speed for time while the star's light presses against it. Photon braking also forces you to fly toward the star in a specific way. You want the sail to face the incoming light to maximize braking. That constrains your trajectory, which can conflict with safe navigation and target selection. It can also conflict with thermal limits. A sail that approaches close enough to get strong photon pressure must survive intense heating and ultraviolet exposure. The same star that helps you brake can also degrade coatings, embrittle materials, and charge surfaces. If you use a laser from home to brake, you face the same diffraction and pointing limits as acceleration. Over light years, keeping a beam on a moving sail is a precision problem at the edge of plausibility. The infrastructure burden returns, just move to the other end. The beam must lead the target, compensate for light travel time, and remain stable despite atmospheric distortion or platform vibration. The farther the craft is, the smaller it looks, and the more perfect your aim must become. Some proposals combine braking methods to share the pain. A craft might accelerate with a home laser, coast, then brake with a magnetic sail and finish with photon pressure near the star. Hybrid designs trade complexity for reduced propellant. In concept art, these hybrids look like transforming machines. Sails unfolding, loops energizing, radiators blooming like metallic petals. Each transformation is a milestone, and each one is also a test that cannot be repeated. Complexity is not a footnote for interstellar missions. Every deployment mechanism is another failure mode. Every extra system must work after decades, when materials have aged and spares are limited. Space is a harsh laboratory for long-term reliability. Polymers outgas, metals creep, lubricants migrate, and radiation slowly changes electronics. Even if nothing breaks dramatically, performance can drift until margins vanish. There is also a deeper constraint that optimistic charts often skip. Braking strategies depend on knowing what you will brake against. You need forecasts of stellar wind, dust density, and magnetic field structure. At interstellar distances, we can infer some properties from telescopes. We can estimate a star's luminosity and activity class. But the local environment is not a static label, it is a dynamic weather system. That weather system has cycles and storms. Stellar winds vary with magnetic activity, and flares can spike particle flux and radiation. If your braking method depends on those particles, then the star's temperament becomes part of your flight plan. A destination star can flare, change wind pressure, and reshape its astrosphere. Dust density can vary with local clouds and debris belts. Magnetic topology can change the effectiveness of a magnetic sail dramatically. Even the boundary regions matter. The astrosphere is where stellar wind pushes against the interstellar medium, forming shocks and turbulent layers. A sail entering that region may see conditions that are nothing like the quiet averages used in early estimates. That uncertainty forces conservative design. You carry margin in sail area, power, and structural strength. Margin adds mass, and mass makes every braking method harder. This is the cruel loop of engineering. You add margin to survive the unknown, and the added mass increases the energy you must shed. Then you need more braking capability, which adds more mass, and the loop tightens again. Navigation uncertainty also couples to braking. If you must begin braking far from the star, you must commit early. Early commitment means you are braking while your knowledge of the target is still incomplete. What if the planet you hope to study is not where ephemerides predicted because of unseen companions or measurement error? What if the dust environment is denser than expected, forcing a different approach corridor? The earlier you commit, the fewer options remain. Course corrections during braking are costly. A sail that produces drag also resists lateral maneuvers. If you discover a hazard late, you may not have the delta V to dodge it. There is a subtlety here that is easy to miss. Braking is not just slowing down, it is steering with constraints. A sail can pull you backward, but it cannot easily push you sideways without sacrificing braking efficiency. Even the concept of orbiting a planet becomes a new hill to climb. To capture into orbit, you must shed additional velocity relative to that planet. If you only match the star's frame, you can still be moving too fast for local exploration. A star-centered rendezvous might still leave you with tens of kilometers per second relative to a chosen world. That is enough to turn a gentle insertion into a high-energy encounter. The mission then faces another delta V bill, paid with propellant, aerobraking, or time. So arrival is not one stop. It is a cascade of velocity matches, each with its own energy and risk. Star capture, planetary transfer, orbital insertion and landing are separate bills. Each bill has its own deadline. Miss the star capture window and you may never return. Miss the planetary transfer and you wait years for geometry to realign. Miss orbital insertion, and your arrival becomes a one-time fly-through after all. For robotic probes, you can accept a narrow window and a single pass. You can build instruments that tolerate high rates and pre-planned sequences. For humans, the mission goal implies time, flexibility, and safety margins. This is why many serious interstellar concepts focus on tiny probes. A gram-scale craft can accept flyby science and still be revolutionary. A human ship must carry a world and still break like a feather. There is also a historical echo in that choice. Early aviation advanced with small, risky craft before it carried passengers routinely. Interstellar exploration may follow the same pattern, with robotic pathfinders mapping the real conditions that human missions would later depend on. The deceleration paradox also reshapes the meaning of travel time claims. A headline might quote a cruise time based on peak speed. The real mission time includes acceleration arcs and braking arcs, which can dominate the schedule. Acceleration and braking are not instantaneous, even with powerful systems. They are phases with trajectories, thermal loads, and operational constraints. When you include them, the short trip often stretches into something more honest and more sobering. If you accelerate hard to 0.1 c, you must also decelerate hard from 0.1 c. If your braking method is weak, you must start earlier and accept longer total duration. The fastest cruise can produce the slowest arrival. This is where the paradox becomes almost philosophical. Speed feels like freedom, yet at interstellar scales, speed can become a trap. The more kinetic energy you carry, the more the universe demands a mechanism to take it away. So the honest timeline is not just distance divided by speed. It is distance divided by a full velocity profile that includes how you stop. Every proposed propulsion system must answer the same question twice. When you hear a proposed engine described as capable of 0.2 c, it is worth asking a quiet follow-up. Capable of 0.2 c in what mission profile, with what payload, and with what plan for arrival? The destination does not care about your peak number. This chapter's limit is not pessimism, it is bookkeeping. Momentum must be exchanged, and the universe does not accept promises as payment. If you cannot brake, you did not travel, you only passed through. We can now state the middle chapter truth clearly. Interstellar travel is not forbidden by imagination. It is constrained by physics, and physics demands symmetry between leaving and arriving. And this symmetry points to the next problem. Even if you could accelerate and brake, the space between stars is not empty in the way your spacecraft needs it to be. The medium you hope to ignore becomes the medium you must survive. Next, we enter the interstellar gap itself. We treat it not as a vacuum, but as a thin minefield of dust, radiation, and erosion. The journey between stars becomes its own environment, with its own hard limits. Even if you can accelerate and brake, the space between stars is not empty in the way your spacecraft needs it to be. Interstellar travel is not only a trajectory problem, because it is also a survivability problem measured in impacts, radiation dose, and accumulated damage. The interstellar medium is thin gas, thin dust, and thin plasma stretched across light years, threaded by weak magnetic fields and shaped by old shock waves. Typical densities are only a few atoms per cubic centimetre, sometimes far less in hot regions, and the numbers feel comforting until you multiply by distance and by speed. A useful image is a ship carving a tunnel through the dark. At 0.1 C, the ship sweeps through a vast volume every second, and that volume contains something, even when instruments call it near vacuum. Over decades, even rare particles become a steady stream of collisions because the medium is sparse but the ship is moving fast enough to turn sparsity into inevitability. Start with the most intuitive danger: dust, because it behaves like a hidden minefield. A grain can be smaller than sand, smaller than pollen, smaller than a cell, and it can still be lethal when the closing speed is relativistic. At interstellar speeds, size stops being comforting, because kinetic energy scales with velocity squared, and velocity is the one parameter you are deliberately making enormous. Energy rises as v squared, and the curve is the same one that made propulsion so expensive in the first place. The same speed that shortens the calendar also weaponizes the environment, turning the darkness ahead into a shooting gallery, where the bullets are almost invisible. In the forward camera view, nothing changes, until a flash of plasma marks an impact that was never seen coming. Make the impact physics intuitive with a simple comparison that stays in the body. A milligram is a speck you can barely feel on your fingertip, a tiny weight that seems beneath notice. At 0.1 C, that speck carries energy comparable to a high explosive charge, and the ship's hull becomes the target surface where that energy must be absorbed. The exact number depends on speed and relativistic corrections, but the lesson does not change. Multiply mass by v squared, and the result grows brutally fast because v is tens of thousands of kilometers per second. When velocities climb into that regime, even tiny masses behave like ordnance, and the distinction between particle and projectile begins to blur. At these velocities, an impact is not a dent, it is a plasma event. Brief, violent, and chemically irrelevant. The grain and the struck surface flash into ionized debris, a crater forms, material spools, and a jet of fragments continues deeper into the structure. The physics resembles hypervelocity, impact testing in laboratories, except the test runs for years, and the target cannot be replaced. Secondary fragments are often the real hazard, because they turn one strike into many. The first hit can transform a single grain into a cone of shrapnel, and that shrapnel can cut wiring, puncture tanks, and seed cracks that grow slowly under vibration and thermal cycling. In a crewed ship, the threat is not only catastrophic penetration, but also the long tail of small injuries to the vehicle. Now scale the problem from one strike to a mission, because time is the multiplier that never stops. The ship's frontal area is a target presented for decades, and probability rises with cross-section even when the medium is thin. Habitats are not needle-thin, radiators are broad, and antennas and sensors are exposed. So the geometry of living in space becomes part of the hazard equation. The interstellar medium is not uniform, and that uncertainty matters more than the average density. There are denser clouds, local bubbles, and regions shaped by past supernovae, where dust and gas can be compressed into filaments. Astronomers map some of these structures through absorption lines and radio emissions, but the map is never perfect at the scale a fast ship cares about. Route planning can reduce risk, but it cannot guarantee a clean corridor, because you are navigating through a dynamic, partially measured environment. Navigation also becomes a shielding problem, since a small change in trajectory can change the density field you traverse. The ship must choose between optimal time, optimal braking geometry, and optimal hazard avoidance, three goals that rarely align. There is a second dust problem that feels counterintuitive, because it is not about grains at all. At high speed, you do not only hit dust, you also hit atoms, and each atom arrives with kinetic energy far above chemical scales. The ship is effectively ploughing through a thin, invisible beam, and the beam's power comes from the ship's own velocity. A single hydrogen atom at 0.1 C is not catastrophic by itself, and it will not punch a dramatic hole in the hull. But it is part of a constant rain that erodes surfaces, implants atoms into materials, and charges insulators in ways that can trigger arcing. Over years, that rain can degrade optics, sensors, and exposed radiators, slowly reducing performance until margins disappear. This is where the phrase, hitting nothing, becomes literal, because the ship can be destroyed by what looks like vacuum. The danger is not density, It is energy per particle, and energy is what your propulsion system has spent decades buying. In the forward direction, the interstellar medium becomes a continuous low-level bombardment that never sleeps. So the first engineering response is shielding, and shielding immediately loops back to mass. A thicker wall reduces penetration and spreads impact energy, and it can also provide thermal inertia and structural stiffness. But every kilogram of shield must be accelerated and then decelerated, and that cost is paid in propellant, power, or both. The rocket equation does not care why you added mass, and it does not offer sympathy for armor. It charges you the same for shielding as for habitat volume, and it charges you again when you need to brake at the destination. Protection feeds back into propulsion requirements, and propulsion requirements feed back into protection, an engineering recursion that punishes optimism. A simple solid bumper plate is the most basic concept, because it is easy to picture and easy to build. Put a thick slab at the front and accept that it will take hits, then design the rest of the ship behind it. This works for small probes, but for humans the needed thickness becomes heavy quickly, and heavy is the one thing interstellar missions cannot hide. A better concept is layered shielding, often called a Whipple shield, and it has a long history in Earth orbit. A thin sacrificial layer sits ahead of the main wall, and the first layer breaks the projectile into plasma and fragments. The spacing lets the debris spread, so the rear wall sees a wider, softer UDA rather than a needle-like punch. By the time the debris reaches the rear wall, its energy is distributed over a larger area, and that reduces the chance of a clean puncture. It also reduces peak stress, which helps against cracking and fatigue, especially when the structure is already aging under radiation and thermal cycling. In visuals, you can imagine a bright flash at the first layer, followed by a widening cone of glowing debris. Whipple shielding is not magic, because it is tuned to a range of particle sizes and speeds. At 0.1 C, the debris cloud can still be energetic enough to punch through, especially for larger grains that carry more momentum. The design becomes a statistical bet. You're not stopping everything, you're reducing the probability of a mission-ending event. Spacing also costs volume and structure, and it changes the ship's silhouette. A large standoff distance increases the effective cross-section, which can increase hit probability even as it improves survivability per hit. It can also complicate thermal control and vehicle layout, because radiators, tanks, and structural trusses must fit within the protective geometry. For crewed ships, designers often propose a dedicated forward shield section, almost like a prow built for punishment. The habitat sits behind tanks, consumables, and structural mass that double as protection, and the ship's interior becomes a layered landscape of materials. Water, food, and waste become part of the radiation and impact budget, life support as armor. This dual use is efficient, but it is not free because consumables get used and used mass changes the shield thickness over time. The ship must manage where mass sits, not only how much mass exists, and that becomes an operational discipline. A tank drained in the wrong order is not just a logistics error, it is a change in the protective profile. Some proposals add a forward dust cloud as active shielding, which sounds almost poetic until you picture the mechanics. Release fine particles ahead of the ship to pre-impact incoming grains, forcing collisions to happen far in front where the debris disperses. In a visualization, the ship rides behind a faint shimmering veil, like a comet tail reversed and pushed forward. This approach has costs and uncertainties, because you must carry the dust mass and replenish it for years. The cloud must stay in front despite the ship's motion and any maneuvering, and it must be shaped by fields or clever release geometry. If the ship changes course, the protective veil can smear or thin, and the safety margin can vanish when it is needed most. A dust cloud can also create its own hazard, which is the irony at the heart of the idea. If the cloud density is too high, it becomes a constant self-inflicted sandblasting, heating the shield and eroding it faster than planned. If it is too low, it does not stop the rare large grains that matter most, and rare is exactly the category that ruins long missions. Electromagnetic deflection is another tempting idea, because it promises protection without hauling meters of material. If you can charge incoming particles, you can bend their paths with fields, and magnetic or electrostatic shields could reduce the flux of charged dust and ions. The dream is a ship wrapped in invisible force, a technological echo of Earth's magnetosphere. The limit is neutrality and momentum, and both limits are stubborn. Many grains are neutral, and neutral objects do not respond strongly to fields, while charging them takes time and interaction. At point 1c, the interaction window is short, so short that the ship may pass the particle before it can be meaningfully influenced. Fields also require power and structure, and those requirements are not abstract. Large magnetic systems mean coils, cryogenics, and radiators themselves must face the same particle rain. Those add mass, and mass again feeds the propulsion bill, so the shield you add to save the mission can help make the mission unaffordable. Even for charged particles, deflection is not always enough, because high-energy ions have large rigidity. They need strong fields over large distances to bend significantly, and the required field volumes can become enormous for the most penetrating components. In other words, the particles you most want to steer are the ones least willing to turn. So impacts are one half of the interstellar medium story, and the other half is radiation, which is not a single thing. It is a mix of galactic cosmic rays, sporadic particle storms, and secondary radiation created inside your own shielding when energetic particles collide. The ship is not only being hit from outside, it is also manufacturing new radiation inside its protective layers. Galactic cosmic rays come from outside the solar system, accelerated by supernova remnants and other violent sources across the Milky Way. They include protons, heavier nuclei, and a small fraction of electrons, and many arrive with energies that make them hard to stop. Some are so energetic that, in practical terms, they behave like microscopic cannonballs that ignore thin walls. For a crew, the key metric is dose over time, and dose is cumulative, like a slow accounting that never resets. A multi-decade cruise means years of exposure with no geomagnetic field and no thick atmosphere, which are the two protections Earth quietly provides. Even moderate flux becomes a serious health risk when integrated over decades, because biology remembers every ionization event. Radiation is not only about cancer risk, and that matters for mission planning and ethics. High-energy particles can damage the central nervous system, increase cataracts, and degrade cardiovascular health, with effects that may appear long after exposure. For a mission that already strains psychology and medicine, radiation becomes a compounding stressor, one more invisible pressure on the body. The ship also carries electronics, and electronics are vulnerable in ways that feel almost fragile. Single event upsets can flip bits and corrupt memory, turning a correct command into nonsense in a microsecond. Long-term displacement damage can change transistor behavior and reduce sensor performance, slowly shifting calibration until the ship's perception of reality drifts. Redundancy can help, but redundancy adds mass and complexity creates new failure paths. Error correction can help, but it adds power and design overhead, and power must be generated and rejected as heat. Every mitigation has a cost that shows up somewhere else in the system, because interstellar engineering is a closed budget with no easy line items. The radiation environment is not constant along the route, and the ship's timeline intersects with changing plasma conditions. Near departure and arrival, the ship is closer to a star, and stellar particle events become relevant in a way deep space crews may not match. Flares and coronal mass ejections can deliver intense bursts of energetic particles, compressing a year's worth of dose into hours. Our sun is a useful warning, and it is also a reminder of how lucky Earth is. Many target stars are more active, especially red dwarfs that can flare frequently and strongly, bathing nearby space in high-energy particles. That means arrival at a habitable zone distance could coincide with a harsh particle climate, forcing the crew to hide when they most want to work. There is also the astrosphere boundary to consider, because a star's wind carves a bubble in the interstellar medium. As you enter another star's wind region, plasma conditions shift, and shocks and turbulence can change particle spectra. The transition can create unpredictable exposure spikes, brief episodes where the environment feels less like empty space and more like weather. Now bring shielding back into the story, because radiation protection is not optional for humans. The simplest approach is mass between crew and space, and hydrogen-rich materials like water and polyethylene are effective against many particles. Hydrogen is useful because it reduces secondary production compared with heavier elements, and it slows particles in a more controlled way. But cosmic rays include heavy ions that punch deep, and they do not politely stop when you ask. To reduce dose significantly, you need substantial aerial density, and the numbers push you toward meters of water equivalent for meaningful reduction. That is heavy, and the ship must carry it not as cargo but as a constant mission-long requirement. This is where the documentary's central question tightens, because the physics refuses to negotiate. Are we physically capable of sending humans within meaningful timescales, and can we keep them healthy enough to matter when they arrive? The answer depends on whether we can afford the mass that keeps them alive, and whether we can afford the propulsion that mass demands. Thicker shielding is not always better, and this is a critical twist that surprises non-specialists. When high-energy cosmic rays hit shielding, they can produce secondary particle showers, neutrons, pions, and gamma rays born inside the material. The shield becomes a target, and the crew sits behind it, listening to the echo of impacts they cannot see. Those secondaries can penetrate deeper than you expect, and their biological effectiveness can be different from the primaries. In some regimes, adding more high-Z material can worsen the dose behind it, because heavy nuclei fragment into a spray of lighter, still energetic particles. Shielding becomes a particle physics problem, not only a construction problem, and the best answer depends on spectra, geometry, and time. So designers consider graded shielding, building a careful stack rather than a single thick wall. Put low-Z materials to slow and fragment ions, then layers that capture neutrons, then structural walls that carry loads. Even then, you are managing trade-offs rather than eliminating risk, because the cosmic ray spectrum includes components that are simply too energetic to stop efficiently. A practical strategy is a storm shelter inside the ship, which is a compromise between mass and safety. Concentrate shielding around a small volume where the crew can retreat during particle events, using water tanks and supplies as a protective ring. This reduces peak exposure, but it does not solve the background dose that accumulates during ordinary days. A storm shelter also changes mission operations because survival becomes part of the schedule. During events, work stops, maintenance pauses, and the crew waits in a cramped space while alarms and monitors track particle flux. Over decades, repeated interruptions become part of the rhythm of survival, an enforced humility before the environment. Active shielding is proposed again for radiation, not just dust, because the appeal is so strong. A magnetic field could deflect charged cosmic rays the way Earth's magnetosphere does, reducing dose without massive walls in principle. In visuals, you might see field lines arcing around the ship, a translucent bubble pushing particles aside. In practice, the field strengths and volumes required are daunting, and scaling is unforgiving. Earth's magnetosphere is planetary scale, and it still lets in high-energy particles at the poles and during storms. A ship-scale field would be smaller and less forgiving, and the most energetic particles would still punch through with little deflection. Strong fields also create engineering side effects that cannot be ignored. They interact with onboard electronics, with plasma around the ship, and with any charged tethers or sails that might be part of propulsion or braking. They can induce forces and torques that must be controlled, so the shield becomes a steering problem as well as a safety system. If the ship uses superconducting coils, it must keep them cold for decades, and that requirement is relentless. Cryogenic reliability becomes life-critical, because a quench event is not only a power failure but a sudden change in protection. In the worst case, the crew could lose shielding at the same moment a particle event arrives, and the margin disappears in minutes. So the mitigation menu fills with partial solutions, each one real and each one incomplete. Whipple shields reduce puncture risk but add structure and mass. And dust clouds might reduce large-grain threats but demand continuous replenishment and careful control. Electromagnetic deflection helps for charged particles, but cannot guarantee protection from neutral grains, while route planning can avoid denser clouds but relies on incomplete maps. Every option carries uncertainty, and uncertainty demands margin, which is the hidden mass that kills optimistic designs. You add thickness for unknown dust, and you add redundancy for unknown failures, and then you add propellant or power to move the heavier ship. The cycle repeats, and the spreadsheet becomes a story about compounding penalties rather than single obstacles. This is the same recursion we saw with propulsion and braking, now driven by the environment instead of the engine. Interstellar space forces you to carry your own atmosphere, your own magnetosphere, and your own repair shop because there is no rescue and no resupply. Each addition makes the ship harder to push and harder to stop, and the medium collects its tax either way. At 0.1 C, even the front shield becomes a consumable, which is a sobering way to think about armour. Impacts erode it, sputter atoms away, and gradually roughen surfaces that once were smooth, and erosion must be budgeted like fuel. The ship must either carry spare shield mass or accept a rising risk curve over time, and neither choice is emotionally comfortable. Repair is not trivial at these speeds, because the forward direction is a hail of energetic particles. You cannot do an external spacewalk while the nose is being peppered, and you cannot casually expose humans to that environment. Maintenance must be internal, remote, or conducted during slow phases if the mission profile allows, and the ship must be designed for access before it ever launches. This pushes designs toward a thick, sacrificial nose and a protected core, with systems arranged like organs behind ribs. The ship becomes less like an airplane and more like a bunker with an engine, and the aesthetics of exploration give way to the geometry of survival. Comfort and openness lose to layered walls, narrow corridors, and carefully placed mass. The interstellar medium also changes what failure looks like, because many failures are quiet at first. A tiny puncture can become a slow leak that is hard to detect against background outgassing, and a microcrack can propagate under thermal cycling until a panel fails. The mission must treat inspection and monitoring as continuous, because the environment does not wait for convenient maintenance windows. Radiation can quietly degrade systems long before a dramatic event, and that slow drift is dangerous. Sensors drift, insulation embrittles, and lubricants change, and the ship's performance can decay in small steps that look like noise. The mission must treat aging as an expected load case, not a surprise, and it must carry the diagnostic tools to notice problems early. So the environment is not a single obstacle. It is a constant tax that accumulates every day. It taxes mass, it taxes power, it taxes reliability, and it taxes time, and those taxes compound because the mission is long. When we talk about meaningful timescales, we must include the time spent surviving the trip, not only the time spent moving. This also reframes the difference between probes and people, and the contrast is stark. A gram-scale probe can accept high risk and short lifetimes, and it can be designed to fail gracefully after a brief data burst. A crewed ship must keep a biosphere stable while being sandblasted and irradiated, and it must do so with a reliability that borders on the unprecedented. And that is the tension this chapter builds toward, because the outside hazards are only the first gate. Suppose we solve propulsion enough to cruise, and braking enough to arrive, and suppose the ship survives the interstellar medium with its hull intact, then the question becomes more intimate and more difficult. Can a living world survive inside the ship for decades without collapse? Can biology tolerate isolation, closed loops, and slow failures that engineering cannot fully predict, especially when the environment is constantly trying to push the system off balance? What does it mean to carry an ecosystem through a place that is not designed for life, and to ask it to remain resilient without sunlight, seasons, or a planet beneath it? The universe keeps making interstellar travel feel less like engineering and more like a belief system, and the feeling is earned. Not because the equations are mysterious, but because the required margins are so large they resemble faith, and because every solution creates new constraints. Honest awe begins when we admit what the medium demands, and we keep building anyway. Next, we leave the outside hazards and move inside the hull, where the most delicate machinery is alive. We ask whether ecology, psychology, and human biology can survive the long crossing, even if the ship can. Suppose the ship survives the interstellar medium with its hull intact. The next limit is not outside the walls, it is the living system inside. Physics can be priced in equations, and engineering can be priced in mass, strength, and margins. Biology is priced in feedback loops that never stop running, even when you are asleep. A crewed starship is not a vehicle with life support. It is life support with a vehicle attached. Closed loop sounds like a clean promise, almost like a slogan you can stamp on a blueprint. Recycle air, recycle water, grow food, turn waste into nutrients. Keep the loop stable for decades, then for centuries, without a single resupply ship. Yet, closed is not a binary switch, because living systems breathe in time. Every loop has delays, storage pools, and hidden pathways, and those pathways do not announce themselves until something drifts. The question is not whether a loop can be drawn. The question is whether it can be governed. On Earth, we tried a version of that promise at full scale. Biosphere 2 was built as a sealed world, designed to test self-sustaining human life. It had sunlight, full gravity, and rescue teams within driving distance. The project rose from a late 20th century mix of optimism and urgency, when space habitats felt near and ecological limits felt close. Engineers and ecologists wanted a testbed that was neither classroom model nor science fiction set. They built a structure that looked like a greenhouse cathedral: steel ribs, glass panes, and airlocks that clicked shut. The goal was simple in words and brutal in practice. 8 people would live inside a closed ecosystem for 2 years, with no routine exchange of air. The system would recycle air and water, grow crops, and model a future habitat off Earth. Biosphere 2 was not a small terrarium, and it was not a single ecosystem. It was a complex of biomes, agriculture, and engineered infrastructure, all forced to share one atmosphere. Rainforest, ocean, desert, savanna, and a farm were packed into one sealed volume. Visually, it was mesmerizing. Condensation beading on glass, mist rising from leaves, and sunlight cutting through humid air. A miniature ocean rolled under a curved roof, while a desert sat a short walk away, its soil drying under the same sky. The crew lived in the seams between those worlds, where pipes and sensors met roots and microbes. The project carried a deeper ambition that matters for interstellar travel. If a closed ecosystem can work on Earth, it might work in transit. If it fails on Earth, the stars do not forgive. Early days inside Biosphere 2 looked like a triumph of planning. The air was breathable, the crops sprouted, and the crew began routines that blended farming with maintenance. Then the system started drifting in ways the designers did not predict, and the drift did not come with alarms. Oxygen began to decline, slowly at first and then alarmingly, like a tide going out. Over months, O2 fell from near normal levels toward values that mimic high-altitude hypoxia. The crew's bodies became the first sensors, because headaches and fatigue arrive before a chart looks dramatic. At lower oxygen, partial pressure, the body compensates by breathing faster and pushing the heart harder, but that compensation has limits. Sleep becomes shallow, exercise becomes punishing, and small tasks feel steep. In a starship, that physiological tax would translate directly into slower repairs and weaker attention. Carbon dioxide did not behave like a simple waste product that rises smoothly with respiration. CO2 swung up and down, sometimes spiking to levels that impaired sleep and cognition. Then it could crash again, driven by plant growth and soil chemistry. Those swings matter because CO2 is both pollutant and plant food, and the balance is delicate. Raise it too high and humans suffer headaches, irritability, and degraded performance. Drop it too low and plants may slow photosynthesis, changing yields and oxygen production in the same breath. The headline lesson was not that plants failed, because many plants grew vigorously. The lesson was that the whole web responded, and it responded non-linearly. A small imbalance did not stay small. It amplified through microbes, soils, and gas exchange. Non-linear means thresholds, points where the same push suddenly produces a larger shove. Ecosystems store carbon in wood, soil, and dissolved pools, and they release it on schedules that depend on temperature and moisture. In a sealed habitat, those schedules become the habitat's heartbeat. One culprit was unexpected microbial activity in the soils. Microbes consumed organic matter and oxygen, producing CO2 faster than models assumed. The soil was alive in ways the spreadsheets did not capture. In plain terms, the dirt was not inert substrate because it was a reactor. Bacteria and fungi decomposed organic material, and decomposition is an oxygen-hungry process. If respiration in the soil outpaces photosynthesis in the leaves, the atmosphere shifts even when the plants look healthy. Another surprise came from the structure itself. CO2 interacted with exposed concrete, forming carbonates and effectively scrubbing CO2 from the air. That sounded helpful, but it also hid the oxygen problem by masking CO2 buildup. Concrete is not just a backdrop because it participates in chemistry. Carbonation reactions can lock carbon into mineral form, and that changes the apparent accounting of gases. In a starship, every material choice becomes part of the life support equation, even if it looks like mere architecture. The system was not only biological, it was a coupled machine of biology and materials, and coupling creates surprises. Walls, seals, concrete, and plumbing became part of the carbon cycle. As oxygen fell, the crew faced a decision that a starship would not have. They could break the seal and add oxygen from outside, trading purity of experiment for human safety. Eventually, oxygen was injected to protect health and keep the experiment running. That moment is the documentary's pivot, because it reveals what closed really means. A closed ecosystem that needs emergency oxygen is not closed. It is a partial loop supported by an external civilization. For a starship, there is no outside warehouse of breathable air. There is only what you carry, what you can regenerate, and what you can afford to lose. When the loop fails in transit, the response must come from inside the loop. Food was the second slow crisis, and it arrived with a different kind of pressure. The farm produced less than planned, and calories became a daily constraint. The crew lost weight, and hunger became a psychological force that shaped every interaction. A closed habitat forces agriculture to be both precise and resilient, which is an uneasy pairing. You must hit yields, but you must also tolerate pests, disease, and equipment failures. On a ship, a missed harvest is not a disappointing season. It is a countdown. Agriculture in a closed habitat is not just planting, watering, and waiting. It is pest control without easy pesticides, pollination without open ecosystems, and soil management without new inputs. Every mistake becomes a persistent condition. Even the simple act of harvesting has system consequences, because biomass is stored carbon and stored nutrients. Remove too much plant matter from the wrong pool, and you change soil structure and microbial balance. Leave too much waste unmanaged, and you invite molds and insects into the air system. Crop yields depend on light, temperature, humidity, and nutrient availability, and each variable has a narrow comfort zone. They also depend on labour, time, and morale, which are harder to quantify. In a closed system, the farm is both life support and full-time job. Inside Biosphere 2, the visuals of farming were almost pastoral. Rows of crops under glass, hands in soil, sunlight on leaves. But the context made it different, because every leaf represented oxygen, calories, and schedule. The crew did not garden for pleasure. They farmed for survival. Biosphere 2 also revealed how quickly ecosystems shift species balance. Some insects exploded in population, while others collapsed. Ants became a dominant force, and the system's intended equilibrium never arrived. In ecology, stability is often a story of checks and balances, where predators, parasites, and competition keep any one species from taking over. In a sealed habitat, those checks can be missing or weakened, and the winners exploit that vacancy. Once a pest population establishes, it can become a permanent resident. Microbial ecology was the invisible engine behind many outcomes, even when the air looked clear. Microbes drive decomposition, nitrification, and nutrient availability. They also drive disease risk, biofilms, and corrosion in pipes and filters. In a starship, microbes are not optional passengers, and they do not stay static. They live in air ducts, on surfaces, in water systems, and in the crew. They evolve under selection pressure, and they exploit every stable niche. Selection pressure is not abstract when the environment is uniform and repetitive. If one strain tolerates disinfectants or low nutrients, it gains an advantage. Over years, the microbial community can drift toward forms that are harder to control, especially in warm, wet plumbing. Closed-loop life support is often explained as 3 boxes, because diagrams like clean boundaries, air revitalization, water recycling, and food production. Biosphere 2 showed that each box leaks complexity into the others. Air revitalization is not only CO2 removal, even though that is the headline metric. It is O2 generation, trace contaminant control, and humidity management. It is also pressure control, fire risk management, and the chemistry of materials off-gassing. Humidity is a quiet variable with sharp edges, because water vapor changes comfort and microbial growth at once. Too much moisture invites mold and corrosion, while too little dries mucous membranes and stresses plants. In a sealed habitat, humidity becomes both a biological and mechanical tuning knob. On today's spacecraft, CO2 scrubbing is handled by chemical sorbents and regenerable systems, which are predictable but consumptive. Oxygen is supplied by stored tanks or electrolysis of water, which ties air directly to the water budget. Those are engineered loops, not ecological loops. They work because missions are short and resupply exists, even when it is expensive. Filters can be replaced, cartridges can be swapped, and unexpected chemistry can be studied on the ground. A starship wants loops that can run for decades without resupply, and that changes the design philosophy. That pushes toward biological oxygen production and food growth, because plants and algae can, in principle, run indefinitely. It also pushes toward robust physico-chemical backups, because biology can crash. The uncomfortable truth is that redundancy must cover both kinds of failure. Water recycling is often treated as solved because we can distill and filter with impressive efficiency. In reality, long-duration recycling is a war against biofilms, trace organics, and system drift. The water loop is a microbial habitat with plumbing. Biofilms are communities that glue themselves to surfaces, and they are stubborn by design. They can foul membranes, alter taste and odour, and shelter pathogens from disinfectants. In a starship, a slimy layer inside a pipe is not a nuisance, it is a threat to reliability. Nutrient cycles are the hardest loop to close, because nutrients are not gases that can be scrubbed and rebalanced easily. Nitrogen, phosphorus, potassium, and micronutrients must circulate without loss, precipitation, or contamination. Waste must be processed into safe fertilizer without pathogens or toxic buildup. Nitrogen is especially tricky because it changes form as it moves through biology. Plants prefer nitrate or ammonium, microbes convert one to the other, and losses can occur as gases if conditions shift. In a sealed habitat, a slow nitrogen leak is not just inefficiency, it is eventual starvation. Waste processing is not a single machine you can bolt to a wall. It is a chain of steps that must be reliable and monitored, because each step creates its own byproducts. Composting, anaerobic digestion, oxidation, and filtration each have failure modes and side effects. Anaerobic processes can generate methane and sulfur compounds, which are energy-rich but hazardous in air. Aerobic processes consume oxygen, which competes with human breathing and plant needs. The best method depends on how the rest of the loop is behaving that month. Biosphere 2 made those failure modes tangible because the crew lived with the consequences. When soils behave differently, nutrients lock up or wash away. When humidity shifts, molds bloom. When CO2 swings, plant growth changes and the whole schedule slips. The core problem is that ecosystems are non-linear control systems, and they are full of hidden state variables. They have delays, thresholds, and runaway states. They can look stable until they cross a boundary, then they move fast. Engineers like systems with clear transfer functions and predictable responses because you can design margins. Ecology offers coupled differential equations with unknown parameters, and many parameters change with time. In a closed habitat, uncertainty is not academic. It becomes a maintenance burden. Monitoring becomes life-critical, not because sensors are glamorous, but because they buy you time. You need continuous sensing of O2, CO2, trace gases, particulates, and microbes. You need soil chemistry tracking, nutrient assays, and water quality analytics. You also need to monitor the humans because physiology is part of the loop. Body mass, sleep quality, infection rates, and stress hormones become operational data. When the crew degrades, the system's ability to respond degrades with them. Monitoring alone is not enough, because information without action is just anxiety. You need the ability to intervene without breaking the loop. That means valves, scrubbers, spare pumps, replacement membranes, and sterilization capacity. Here the mass problem returns in a new form, because robustness has weight. Robust closed ecosystems demand buffers and redundancy, and those are physical things you must launch. Buffers mean stored oxygen, stored water, and stored food. Redundancy means duplicate processes and spare parts. Every buffer adds payload mass, and every redundant subsystem adds power draw and heat. Interstellar design already struggles with shielding, radiators, and braking. Closed-loop robustness pushes the ship heavier again. A fragile ecosystem is light but risky, like walking a tightrope with no net. A robust ecosystem is heavy but still uncertain, because complexity does not disappear when you add hardware. Interstellar travel forces a choice between mass you cannot afford and risk you cannot accept. Biosphere 2 also exposed the human factor under closed conditions, and the exposure was relentless. The crew lived under constant scrutiny, constant labour, and constant awareness of limited resources. Small conflicts became structural. Imagine the visuals: narrow corridors between biomes, the same faces at every meal, and the same tasks waiting every morning. Outside the glass, the world continued, but inside the air was shared and finite. In that setting, a disagreement is not just emotional, it is operational. Social stress was not a side story, because it feeds back into performance. It was a system variable that changed outcomes. When trust breaks, maintenance slips. When morale drops, farming suffers. When sleep is poor, mistakes multiply. In a starship, the crew cannot rotate out, and there is no relief valve of distance. There is no fresh team arriving with new energy and new social dynamics. The same people must carry the loop, repair it, and live inside its consequences. Closed ecosystems also create ethical pressure because scarcity turns choices into moral weight. If the system drifts toward failure, who decides rationing, risk, and intervention? Governance becomes part of life support because decisions change survival odds. Biosphere 2 had external managers, media attention, and internal disagreements about control and authority. That tension mattered because it shaped interventions and trust. A starship will have delays measured in years, not meetings, and those delays harden autonomy. The lesson is not that Biosphere 2 was foolish, because the attempt was serious and historically rare. The lesson is that it was the best warning we have at scale. If a sealed habitat struggles with sunlight and rescue nearby, interstellar isolation multiplies the stakes. A starship ecosystem must run longer than any human experiment has ever run, which makes time the dominant stressor. It must survive generational turnover, equipment aging, and microbial evolution. It must do so while the ship is being irradiated and slowly damaged. Time is the hidden amplifier, because small errors compound like interest. Small leaks in nutrients, small losses in water, and small inefficiencies in recycling accumulate. Over decades, a 1% loss per year becomes a cliff. Even if mass balance is perfect on paper, real systems have entropy and wear. Filters clog, membranes foul, sensors drift. Calibration becomes a ritual, and the ritual must survive boredom and fatigue. In long missions, the most dangerous failure mode may be normalization, when gradual decline becomes the new normal. If a gauge reads slightly off for months, people stop reacting. A closed ecosystem punishes that complacency, because the bill arrives late and large. This is why closed-loop life support is not a gadget you install and forget. It is an operating culture that must be taught and maintained. It requires expertise across ecology, chemistry, medicine, and engineering, and it requires constant training. A starship must carry that expertise inside the crew, and it must carry it across generations. That means education systems, documentation, and institutional memory that can survive accidents and politics. The ship becomes a traveling civilization, not a mission. Spare parts become a biological requirement because hardware failure quickly becomes metabolic failure. If a pump fails, crops die. If a sterilizer fails, water quality degrades. If a sensor fails, you may not notice drift until symptoms appear. Manufacturing on board can reduce spare mass, but it adds complexity and new dependencies. Printers need feedstock, tools need calibration, and quality control must be strict. A bad part in a closed loop can trigger cascading failures. The ecosystem also interacts with radiation and shielding choices, which means design decisions cannot stay in separate departments. Water used as radiation shielding is also drinking water and thermal mass. If you consume it or move it, you change protection and temperature stability. Thermal control couples back into biology, because heat is not just comfort. Plants need stable temperature and humidity, and microbes respond quickly to warmth. Waste heat from reactors or electronics must be rejected, and radiators are vulnerable to damage. So the closed ecosystem limit is not separate from earlier limits, because the constraints interlock. More shielding increases mass, which increases energy, which increases waste heat, which stresses thermal control, which stresses biology. The limits stack. Biosphere 2 showed that even with abundant solar energy, managing that stack is hard. A starship may not have sunlight, or it may have weak sunlight between stars. Artificial lighting demands power, and power demands radiators. If you choose nuclear power, you gain reliability but add heat and radiation management, which must be engineered with care. If you choose solar, you lose power density and phase degradation over time. Either way, the ecosystem depends on an energy system that must not fail. A closed habitat also has to manage trace chemistry, the small molecules that accumulate quietly. Volatile organic compounds from plastics and adhesives can build up. Ammonia, methane, and sulfur compounds can appear from waste processing. On Earth, we vent and dilute without thinking, and the atmosphere forgives our laziness. In a sealed world, every molecule stays until processed. Air chemistry becomes a long-term bookkeeping problem, not a comfort setting. Biosphere 2's oxygen decline became famous, but the deeper story is fragility under slow change. The system did not collapse in one dramatic moment. It drifted, and the drift forced interventions. That drift is what interstellar travel cannot tolerate because intervention options shrink with distance. A starship cannot rely on emergency oxygen deliveries. It cannot call a ground team to redesign the scrubbers. It cannot end the experiment when the data get messy. So, self-sustaining must be redefined, and the redefinition is sobering. It does not mean untouched by humans, like a museum exhibit behind glass. It means actively managed by humans who understand the system and can repair it. Sustainability is not absence of work. It is work that can continue. This is where ore becomes heavier and more honest, because the engineering problem becomes a civilization problem. We're not asking whether we can build a sealed box. We're asking whether we can carry a living planet fragment across a light-year gulf, and even if the ecosystem can be engineered, the humans inside it are not interchangeable components. They age, they grieve, they form factions, and they make meaning. The next limit is not only ecology, it is the nature of the crew. Transition. If closed ecosystems are fragile under Earth conditions, then a multi-generational starship must treat sociology and biology as primary engineering disciplines. The next chapter follows the human cargo itself and the costs of time. Even if propulsion, braking, shielding, and ecology are solved, the hardest variable remains people. Interstellar travel turns human biology into a long experiment, and experiments have failure rates. In the vacuum between stars, there is no clinic down the hall, no medevac, and no quick redesign. The body becomes a system under continuous stress, and the margin for error shrinks with every passing year. The central question sharpens here. Are we physically capable of sending humans to another star on meaningful timescales? Or does biology make the timeline irrelevant? A mission can be technically possible, and still be biologically self-defeating, because the travelers arrive diminished, dependent, or unable to function. When we picture a starship crossing a black ocean, we should also picture cells dividing, bones remodeling, and minds adapting, sometimes in the wrong direction. A generation ship is not a vehicle with passengers. It is a moving population that must remain healthy, fertile, skilled, and governed for decades or centuries. That population is also the maintenance crew, the medical staff, the teachers, and the legislators. Every subsystem depends on human attention, and attention depends on sleep, mood, and long-term cognitive stability. Start with radiation, because it is the background tax that never stops charging. Beyond Earth's field and atmosphere, dose accumulates with every hour of cruise. On Earth, our magnetosphere deflects many charged particles, and the thick air absorbs much of what remains. In deep space, the shielding is whatever you brought with you, and whatever you are willing to pay for in mass. Space agencies already set lifetime dose limits, because cancer risk rises with cumulative exposure. Those limits were built for months, not for multi-decade transit. They also assume a certain ability to monitor, to rotate crews, and to return to Earth if needed. A starship cannot rotate its crew with another planet, and it cannot schedule a rescue. At interstellar speeds, shielding competes with propulsion, and the trade never disappears. More mass reduces dose but increases energy needs, heat rejection, and failure surface. A thicker wall is not only heavier, it is more structure to inspect, more joints to seal, and more area where micrometeoroid damage can hide. When engineers add shielding, they also add the burden of accelerating it, breaking it, and keeping it intact for generations. Galactic cosmic rays are not a single hazard you can wait out. They include high-energy heavy ions that punch through materials and fragment into secondary showers. These are nuclei of elements like iron, moving so fast that they behave like microscopic bullets. When they strike shielding, they can shatter atoms and create cascades of new particles that spread dose deeper into the habitat. Solar particle events complicate the picture with bursts that are intense and unpredictable. A ship can build a storm shelter with extra shielding, but the crew must reach it in time. That means alarms, drills, and a culture that treats radiation warnings like fire warnings. Over decades, even a small lapse in discipline can become an avoidable tragedy. Cancer is the headline risk, but it is not the only risk that matters operationally. Radiation can drive cataracts, cardiovascular damage, and possible neurocognitive decline. A cataract is not just a medical diagnosis. It is a reduction in the ability to read instruments, inspect welds, and notice fine cracks. Cardiovascular damage is not an abstract statistic. It is fatigue, reduced endurance, and higher risk during emergencies. The neurocognitive question is especially corrosive for long missions. If attention, memory, or mood drift even slightly, maintenance culture and safety margins erode. A starship is an environment where tiny mistakes can propagate, because systems are tightly coupled and spare capacity is limited. One missed checklist step can become a coolant leak, and one ignored alarm can become a cascading shutdown. Radiation biology makes this harder to model, because the damage is not uniform. High-energy particles can cause dense tracks of ionization that break DNA in complex ways. Cells can repair some of this, but repair is imperfect, and the errors accumulate. Over years, the ship is not only traveling through space, it is traveling through probability. Immune function also changes in space, and the pattern is not reassuring. Stress hormones, altered sleep, and microgravity shift immune signaling and viral reactivation. Latent viruses that most adults carry quietly can reappear when the immune system is distracted. In a closed habitat, that reactivation is not a personal inconvenience. It is a crew-wide operational risk. A closed habitat concentrates exposure to the crew's own microbes. If immunity weakens while pathogens adapt, minor infections can become chronic operational problems. Microbes evolve quickly, and they evolve toward whatever environment you give them. If the ship's surfaces, air filters, and water loops become a stable ecosystem, then biology becomes part of the infrastructure. Now add the musculoskeletal bill that low gravity imposes. In microgravity, bone density declines, muscles atrophy, and connective tissue weakens without constant countermeasures. Bone is living tissue that responds to load, and without load it sheds mineral like an unused scaffold. The loss is not only in mass, it is in architecture, making bones more fragile under sudden forces. Exercise is not a wellness choice on a starship. It is a life support subsystem that consumes time, equipment mass, spare parts, and crew compliance. Treadmills, resistance machines, and harnesses must be maintained like pumps and valves. The crew must also believe in the routine, because the benefits are delayed while the discomfort is immediate. Cardiovascular changes follow the fluid shift of weightlessness. The heart remodels, blood volume drops, and orthostatic intolerance appears when gravity returns. In microgravity, fluids redistribute toward the head, changing pressure in the eyes and sinuses. Over time, the body adapts to a new normal, and that adaptation becomes a liability when conditions change. A mission that arrives at a planet must assume a gravity transition. If the crew cannot stand, walk, or work on arrival, the mission fails after success. The first days on a new world are the most demanding, because infrastructure is minimal and surprises are guaranteed. A crew that is medically compromised is a crew that cannot build, repair, or respond. Artificial gravity is the obvious mitigation, but it is not free. Rotation demands large radii or high spin rates, and both create engineering and human factor penalties. The physics is simple. To get Earth-like gravity, you need either a big ring or a fast spin. The human experience is not simple, because inner ears, coordination, and nausea do not negotiate with equations. Small radius rotation can provoke motion sickness and coordination errors. Large radius rotation increases structure mass, bearing complexity, and the area exposed to impacts. A small habitat makes the gravity gradient steep, so your head and feet feel different forces. A large habitat makes the ship more like a city in space, bigger, heavier, and harder to protect. Even the act of moving inside a rotating habitat has consequences. When you turn your head, the Coriolis effect can create unexpected sensations and missteps. A stumble is not just embarrassing, it can be a broken wrist, a lost tool, or a damaged panel. Over years, those small incidents add up, and they shape the ship's culture of caution. Partial gravity is a tempting compromise, but it is also a biological unknown. We do not know the threshold that preserves bone, pregnancy outcomes, or child development. Mars gravity might be enough for some systems and not enough for others. Without data, every choice is a bet placed on the bodies of future people. Long missions also face the slow grind of aging. A crew that launches in their 20s becomes a geriatric population before arrival at 0.01c timescales. Even if the ship is safe, time is not neutral, and biology keeps its schedule. The mission plan must account for arthritis, declining vision, and the increasing probability of stroke and cancer. Medicine can extend health span, but it cannot erase time. Chronic disease management becomes routine, and routine care must be delivered without a hospital supply chain. That means diagnostics that can be repaired, drugs that can be synthesized or stored reliably, and clinicians trained to improvise. It also means that medical errors become more consequential, because second opinions are limited. This is where the earlier limits converge. Every kilogram of medical redundancy is another kilogram to accelerate, shield, cool, and break at the destination. A pharmacy is mass, but so is the equipment to manufacture drugs, sterilize tools, and image internal organs. The ship becomes a balancing act between what is ideal medicine and what is feasible engineering. Reproduction turns these biomedical risks into ethical landmines. A multi-century mission requires births, which means pregnancy, delivery, and childhood in altered gravity and radiation. The ship is not only transporting adults, it is creating humans in an environment that evolution never prepared us for. That is a profound shift from exploration to inheritance. We have almost no direct data on mammalian gestation in sustained microgravity. What exists is limited, ethically constrained, and hard to generalize to humans. Animal studies suggest that development can be sensitive to gravity cues, but results vary by species and by experimental design. For humans, the stakes are higher and the acceptable error rate is lower. Fetal development is exquisitely sensitive to environment. Radiation, nutrition, stress, and mechanical loading shape organs, bones, and the brain. Early development is a choreography of signals, and small disruptions can have lifelong consequences. In a sealed habitat, even subtle shortages, like trace minerals or certain amino acids, can become systemic. A starship cannot run controlled trials on children to learn what works. The only way to find out is to risk real lives, and that is the moral trap. On Earth, medical uncertainty can be managed with oversight, diverse populations, and the option to stop. On a ship, the population is small, the oversight is internal, and stopping may not be possible. Even if pregnancy is possible, the developmental baseline may shift. A child raised in low gravity may not tolerate Earth-like gravity, making return or surface work uncertain. Muscles and bones develop in response to the loads they experience, and those loads would be different from birth. The child's normal might be incompatible with the destination's demands. Puberty, immune maturation, and neurodevelopment could also diverge under isolation. Education and socialization would happen inside a sealed culture with no outside reference. The ship would be the horizon, the sky, and the weather, and that shapes psychology in ways we can only approximate. What does adolescence look like when there is no outside, only corridors and airlocks? Contraception and family planning become governance issues, not private choices. Population size controls life support load, genetic health, and social stability. If the ship's farms have a bad year, births may need to slow, and that decision becomes political. If the ship's population dips after an accident, births may be encouraged, and that pressure becomes personal. That leads to population genetics, the quiet math behind survival. A tiny founding crew risks inbreeding, loss of diversity, and accumulation of deleterious mutations. Inbreeding increases the chance that harmful recessive traits pair up, and the effect is magnified in closed populations. Over generations, genetic health can decline without any dramatic event. Minimum viable population is not one number, and it depends on assumptions. It depends on fertility rates, mortality shocks, social structure, and how strictly reproduction is managed. A population that is too small is vulnerable to randomness, because chance becomes a dominant force. A single outbreak or a single mechanical disaster can reshape the entire future. Small populations suffer genetic drift, where random chance reshapes the gene pool. Over centuries, drift can be as dangerous as any single accident. Traits can disappear even if they are beneficial, simply because the carriers had fewer children. The ship's gene pool could narrow quietly, then reveal its fragility when conditions change. Avoiding inbreeding implies either a large starting population or stored genetic diversity. Both options increase mass, complexity, and the ethical weight of reproductive control. A larger population needs more habitat volume, more food production, and more redundancy. Stored diversity needs reliable cryogenic systems, careful records, and rules that people accept. Cryopreserved embryos and gametes could expand diversity, but they require long-term storage reliability. They also raise questions about parentage, consent, and social legitimacy. Who decides when an embryo is used and under what criteria? How does a society define family when genetics can be drawn from a library? History offers uncomfortable parallels because attempts to manage reproduction on Earth have often been coercive. A starship would face the same temptations, amplified by scarcity and by the rhetoric of survival. Even well-intentioned policies can become instruments of control when resources tighten. The ship's moral identity would be tested not once, but continuously. If the ship carries thousands to reduce genetic risk, the ecological problem grows again. More people mean more air, water, food, waste processing, and spare capacity. The habitat becomes louder, warmer, and more complex with more points of failure. The very solution to genetic fragility can increase mechanical fragility. If the ship carries hundreds, governance becomes more fragile. A single epidemic, accident, or conflict can collapse the population below a recoverable threshold. In a small community, every specialist matters, and the loss of a few key people can create a competence gap. The ship can survive hardware failures, but it may not survive skill failures. This is the moment where the romantic arc image breaks. A generation ship is not a brave family on a long voyage. It is a high-stakes demographic system. It is also a psychological system because morale and identity influence compliance, learning, and maintenance. The ship must keep not only bodies alive, but also a shared willingness to keep going. Now move from bodies to society because society is also life support. Over decades, mission purpose becomes a story that must be taught, defended, and updated. A story is not propaganda by default. It is a framework that explains why sacrifices are required. Without that framework, the ship becomes a place where rules feel arbitrary and burdens feel unjust. The founding generation can consent to risk, but they cannot consent for their descendants. Children born aboard inherit constraints they never chose, including irreversible separation. That separation is not a poetic metaphor. It is a physical fact measured in light years. The ship's walls become the boundary of their entire lived world. That separation is not only physical, it is informational and emotional because messages take years and answers arrive after lives have changed. A question sent to Earth might be answered after the sender has aged, or died, or changed their mind. The delay turns dialogue into archaeology, and it can make Earth feel like a myth. The opening hook returns with new force. We keep promising the stars, yet the human cost makes the promise feel less like engineering and more like belief. Belief can be powerful, but it can also fracture when reality contradicts expectations. What happens when the ship's children ask why they must risk their lives for a destination they did not choose? Governance drift is the predictable outcome of time and distance. Rules written for launch conditions will face new realities, new leaders, and new incentives. A constitution designed in optimism may meet decades of repairs, rationing, and fatigue. Over time, the ship's legal code becomes either a living system or a brittle relic. A ship needs legitimacy that survives turnover. If authority is seen as inherited, coercive, or outdated, compliance drops and conflict becomes structural. Legitimacy is not only about elections or titles, it is about trust that decisions are competent and fair. In a sealed habitat, a legitimacy crisis is not a headline. It is a threat to oxygen and water. Some designs imagine strict constitutional systems, others imagine technocratic management. Both must survive boredom, crisis, and the temptation to rewrite rules for advantage. Technocracy can drift into elitism, and constitutionalism can drift into paralysis. The ship must also handle emergencies when speed matters more than debate. Conflict resolution cannot rely on external courts or rescue. The ship must contain its own justice system, its own enforcement, and its own mechanisms for reconciliation. Punishment is complicated when every person is a scarce resource, and exile is impossible. The goal cannot be only deterrence. It must also be restoration, because the community has to keep functioning. Resource scarcity sharpens every disagreement. When food yields dip or equipment fails, politics becomes arithmetic, and arithmetic becomes personal. A ration cut is not an abstract policy. It is hunger, stress, and resentment. A maintenance delay is not a scheduling issue. It is a risk that everyone shares. Education continuity becomes a mission-critical subsystem. Every generation must learn engineering, medicine, agriculture, and governance, or the ship loses competence. Training is not a one-time program, it is a perpetual pipeline. If the pipeline breaks for even one generation, the ship may never recover its technical depth. Knowledge is not only stored in manuals, it is stored in habits, tacit skills, and institutional memory that can vanish after a few bad decades. A manual can describe a repair, but it cannot fully transmit judgment, intuition, and the feel of a system under stress. The ship must therefore preserve mentorship, apprenticeship, and a culture of careful work. A ship must plan for cultural evolution, not pretend it will not happen. Language shifts, values shift, and the meaning of the mission can be renegotiated. Traditions will emerge around meals, holidays, and the rhythms of maintenance. Over time, the ship's people may see themselves not as travelers, but as natives of a constructed world. If the destination is abstract to those born in transit, motivation can decay. The ship can become a world, and arrival can look like an unnecessary risk. The outside might be framed as dangerous, contaminated, or morally suspect. In that framing, staying aboard is not failure. It is prudence. That is mission purpose drift in its simplest form. The goal that justified sacrifice at launch may not justify sacrifice 2 centuries later. The original mission statement may sound like an antique speech, disconnected from lived experience. The ship's leaders would then face a question with no easy answer. Why continue? The crew might choose to slow down, change targets, or stop trying to land at all. From the outside, that looks like failure, but from inside, it can look like autonomy. A society that has never seen Earth may not accept Earth's priorities. The ship's people may decide that survival and stability matter more than a promised planet. This is why generation ships are unprecedented ethical experiments. They bind future people to a plan, then ask them to maintain it under conditions of total dependence. Dependence changes moral calculus, because choices are constrained by life support and by the actions of others. The ship becomes a mirror that reflects our values back at us, sometimes harshly. Ethics is not an add-on chapter to the engineering. It is a design constraint that decides whether the mission is permissible, not only whether it is possible. A design that works on paper can still be unacceptable if it relies on coercion or predictable harm. The question is not only can we, but should we, and under what safeguards? Consent is the first fault line. You can volunteer for a one-way trip, but you cannot ethically draft your grandchildren into the same contract. The ship's children are born into obligations they did not sign, and that matters. A society that ignores that fact may remain stable for a while, yet stability is not the same as justice. Risk is the second fault line. A mission can accept danger for explorers, but what level of cancer risk is acceptable for children who never opted in? On Earth, we regulate exposure for workers, and we treat children as a protected class. In deep space, the ship would be both workplace and home, collapsing those categories into one. Control is the third fault line. Preventing genetic collapse may require reproductive rules that feel like coercion, even if they are mathematically justified. The tension is unavoidable, because biology does not care about political ideals. The ship would need policies that are effective, and it would need legitimacy strong enough that people accept them. Privacy, autonomy, and family life become negotiable under survival pressure. The ship can drift toward surveillance and control, because control looks like stability. Sensors that monitor air quality can also monitor movement, and medical records can become tools of governance. The line between safety and intrusion can blur without anyone noticing at first. Yet too much control can trigger rebellion, sabotage, or quiet non-compliance. A stable society must balance freedom with survival, and balance is hard under scarcity. If people feel trapped, they may stop cooperating in small ways, skipping exercise, ignoring protocols, hoarding supplies. Small non-compliance can be as dangerous as open conflict. Psychology is the constant load beneath every policy. Isolation, monotony, grief, and the knowledge of no return can reshape identity and behavior. The starfield outside the window can be beautiful, but it can also be indifferent, a reminder of distance. Over years, even resilient people can develop depression, anxiety, or apathy. People cope by creating meaning, but meaning can diverge. New religions, new myths, and new politics can form around the ship itself. The ship's founders might be remembered as heroes or as captors depending on how life unfolds. Symbols that unify one generation can divide the next. Even if violence never erupts, slow social fracture can be enough. Trust can erode, maintenance can slip, and small errors can compound into system failure. A habitat can tolerate a few broken relationships, but it cannot tolerate a broken safety culture. The most dangerous failure mode may be gradual normalization of shortcuts. This is the brutal reality of the human cargo. We are not designed for centuries in a sealed cylinder, and we cannot test the full scenario in advance. We can simulate pieces, and we can study analogues on Earth, yet the integrated system remains unproven. The first true generation ship would be a leap taken without a net, so the documentary's stance becomes clearer. Interstellar travel is not forbidden by imagination, but it is constrained by physics, biology, and time. The constraints do not merely add difficulty, they change what the mission is. What looks like a voyage becomes a long-term civilization project, with all the fragility that implies. If we insist on sending humans anyway, we must admit what we are building. It is not a ship that carries people, it is a society that carries a ship, and that society must preserve competence, health, and legitimacy while drifting through darkness, without reinforcement, without rescue, and without the option to start over. Transition. After stacking these costs against easy human travel, we turn to the proposals that claim to thread the needle, and we test their promises. We ask which concepts reduce the human burden by changing the timeline, changing the payload, or changing what counts as a human mission. Because the universe does not only demand engines and shields, it demands that the travellers remain human when they arrive, and that demand may be the hardest limit. After stacking distance, energy, braking, ecology, and biology, the pitch always arrives. Here is the breakthrough, here is the engine, here is the plan. In glossy renders, the ship is already halfway there, a bright line crossing a dark map. In the real universe, every line hides a ledger, and every ledger demands payment. This chapter treats the famous concepts with respect and rigour, because they are serious attempts to face a brutal problem. We keep what they genuinely solve, and we name what they ignore because omissions are not neutral. We also surface what they silently assume, about industry, coordination, and the patience of societies. The central question tightens into a practical test that any viewer can understand. Can any proposal move from inspiring diagram to a human arrival within a meaningful timescale without outsourcing the hardest steps to magic? When a design claims a speed, we ask what it costs. When it claims an arrival, we ask how it stops. Start with the idea that sounds most modern, because it is deliberately small and deliberately narrow. Breakthrough. Starshot proposes gram-scale sailcraft pushed to about 0.2 C, using a powerful laser array. The visuals almost sell themselves: an impossibly thin sail, a bright beam, and a tiny starship becoming a fast-moving pixel. At 0.2 C, Proxima is roughly a 20-year cruise in Earth time, ignoring the acceleration and coast details. That is a humanly meaningful timeline, but only for something that weighs grams, not for something that carries air, water, and shielding. The proposal's elegance is that it refuses to pretend otherwise. Starshot's move is to shift mass off the spacecraft, which is the oldest trick in propulsion, applied in a new way. The propellant is not carried, and the energy is delivered by a remote beam, so the craft stays light. In rocket terms, it dodges the rocket equation for the payload, but it does not erase the bill. It relocates the bill into infrastructure that must exist on Earth or in near-Earth space before the first launch. The laser concept implies multi-gigawatt to terawatt-class power during the firing window, sustained with extraordinary stability. It implies an optical phased array of extreme size and coherence, acting like a single, gigantic instrument. To picture that, imagine a continent-scale field of emitters, each one phase-locked like musicians in a perfect orchestra. The timing errors tolerated are not milliseconds but fractions of a wavelength, hundreds of nanometers, because phase is the steering wheel. The array is not merely bright, it must be precisely shaped, so the beam stays tight far beyond the moon. Diffraction sets the first hard geometry, and it is indifferent to ambition. A beam spreads with distance, so the array must be huge to keep the spot tight on the sail, especially as the craft races away. In simple terms, a small flashlight cannot paint a dot on a distant mountain, and a starship's sail is a dot. Pointing sets the second hard geometry, and it is even less forgiving. The sail is tiny, the target is light years away, and the beam must stay locked through atmospheric and mechanical noise. In the visuals, the beam looks like a rigid rod, but in physics it is a wavering cone. Even if the array is in space, the control problem remains brutal, because structures flex and systems vibrate. Nanoradian errors become misses, and misses become wasted power, while the sail drifts out of the beam's center. Jitter becomes torn sails because uneven illumination turns a smooth push into a twisting shove. Then the sail itself becomes the mission, not a footnote. It must be ultralight, reflective, and thermally resilient under an intense beam, while keeping its shape like a mirror. The sail is also a control surface, because its geometry determines stability, and stability determines whether the craft stays in the beam. Absorption that looks negligible on paper becomes lethal at these intensities. A fraction of a percent turns into heating that can warp, buckle, or vaporize, because the beam's power density is concentrated. Heat does not politely distribute itself, and thin films have little thermal mass to buffer spikes. To make that vivid, imagine a soap bubble under a blowtorch, except the bubble must remain perfectly smooth. The sail must dump heat by radiation, which scales with temperature and emissivity, so material choices become destiny. A coating that reflects well but radiates poorly can trap heat like a blanket. Acceleration loads are not gentle, and the numbers are easy to underestimate. A gram craft reaching 0.2 C over minutes implies tens of thousands of G, which constrains electronics, solder joints, optics, and any moving parts. Even if the craft is a wafer, the bonding between layers becomes a structural question. The sail must also remain stable in the beam, because stability is thrust direction. Any tilt changes the force vector and the craft can tumble out of the beam in seconds, ending the acceleration phase early. The control solution is subtle. Shape the sail so the beam naturally recenters it, like a marble in a bowl. Starshot therefore assumes advanced materials, precise fabrication, and control at microscopic mass budgets, where every milligram is argued over. It also assumes a data system that survives acceleration and radiation, because space is not empty at these speeds. At 0.2 C, a dust grain is not a speck, it is a bullet. That dust hazard is not science fiction, and it is not merely about catastrophic hits. Even tiny impacts can pit optics, erode surfaces, and generate plasma that interferes with electronics. The craft's frontal area must be minimized, but the sail is a large target during acceleration, which creates a design tension. Then comes the quiet constraint that changes everything, because it shapes what success even means. Starshot is a flyby, and at 0.2 C the target system is a brief encounter, not a visit. The probe does not enter orbit, does not linger, and does not break into a stable vantage point. A probe crosses an astronomical unit in about 40 minutes at that speed, which is barely enough time to breathe. The best images and spectra must be captured, processed, and transmitted quickly, because the geometry changes minute by minute. The camera is not taking postcards, it is sampling a storm of photons under a deadline. That forces a different philosophy of instruments, closer to high-speed ballistics than to planetary reconnaissance. Exposure times are short, pointing must be predictive, and onboard autonomy becomes essential, because Earth cannot steer in real time. Light itself takes years to carry commands, so the craft must decide what matters as it passes. Communication is another hidden scaling, because the downlink is where tiny payloads pay a heavy tax. A gram craft cannot carry a high-gain dish with deep power reserves, so the downlink becomes a major challenge. The signal must cross light years, and it must compete with the noise floor of space and Earth's own radio environment. In practice, that implies narrow beams, precise pointing, and long integration times on Earth, using large receiving arrays. The craft's transmitter must be efficient, and its clock must be stable, because drift smears data across frequencies. Even the act of turning the transmitter on is a power budget decision. Starshot is honest about its ambition when read carefully, and that honesty is part of its value. It aims to send cameras and sensors, not people, and it aims to prove interstellar reach, not interstellar settlement. It is a technological proof, not a migration plan. That is not a failure of imagination, and it is not a retreat from wonder. It's a recognition that grams can be accelerated by beams, while tons demand an entirely different civilization, with different risks. The concept draws a bright boundary line between possible experiment and possible society. Now widen the lens to the classic study that tried to move beyond grams into something that resembles a true interstellar vehicle. Project Daedalus remains the most cited serious interstellar vehicle concept, partly because it did the unglamorous work. It quantified masses, staged engines and failure modes, and it did so without claiming miracles. Daedalus is fusion pulse propulsion, a cousin of controlled explosions rather than steady flame. It throws small fusion explosions behind a pusher system, converting fusion energy into directed exhaust momentum. In the mind's eye, you see a rhythmic strobe of detonations, each one a hammer strike on a magnetic nozzle. The study targeted about 0.2 C for an uncrewed probe to Barnard's star, a nearby red dwarf with a long history in astronomy. It accepted a decades-long cruise and a high-energy, high-mass vehicle, because speed is bought with energy. It also accepted staging, because even fusion cannot escape mass ratios. The first stage accelerates the second, and the second carries the payload onward, shedding dead mass along the way. Staging is not an aesthetic choice. It is a mathematical concession to exponential penalties. Every kilogram of tank and engine you carry to the end is a kilogram you must accelerate for the entire burn. The mass scale is the first shock, and it changes the emotional tone of the design. Daedalus is not a ship you launch, and it is not a vehicle you assemble in a hangar. It is an industrial product measured in tens of thousands of tons, closer to a floating refinery than to a spacecraft. Most of that mass is propellant, because momentum must come from somewhere, and conservation laws are not negotiable. Even with high exhaust velocity, you still need enormous reaction mass, because the ship must throw something backward to go forward. Fusion helps by increasing exhaust speed, but it does not make reaction mass disappear. The propellant choice reveals the second shock, and it is a geopolitical as well as technical assumption. Daedalus assumed helium-3 for fusion, because it reduces neutron radiation and improves performance compared to deuterium-tritium. In plain language, it is a cleaner burn, but it is also a rarer fuel. Helium-3 is rare on Earth, and it is not sitting in convenient tanks waiting to be used. The study therefore leaned on mining it from the outer planets, often imagined from the atmospheres of Jupiter or Saturn, where trace concentrations exist. That assumption is not a small footnote, because it implies a mature solar system economy. It implies heavy industry, deep space logistics, and energy budgets beyond today's scale, operating far from Earth's easy resupply. Mining helium-3 is not like digging coal, and it is not like pumping oil from a well. It means processing vast volumes of gas to extract trace fractions, then storing and transporting cryogenic fuel across millions of kilometers. To visualize that, imagine orbital factories skimming a giant planet's upper atmosphere, dipping like seabirds into a storm. Tankers spiral outward, their holds filled with supercold gas, while automated refineries separate isotopes with patient industrial precision. The romance of the Starship is preceded by decades of unseen infrastructure. Daedalus also assumed reliable pellet injection, ignition, and magnetic nozzle behavior at unprecedented repetition rates. It assumed a reactor that is also a rocket engine, which is a category of machine humanity has never built. Each pellet must arrive on time, ignite predictably, and release energy in a controlled geometry. The gap between paper and buildable industry is the real Daedalus lesson, and it is why the study still matters. The physics is not obviously wrong, but the readiness level is near zero, and that is not an insult. It is simply what never built before means when the required duty cycle is years. Neutron flux, erosion, and activation would punish the engine structure, because high-energy particles damage materials at the atomic level. Waste heat would demand radiators that survive decades of impacts and degradation, because you cannot hide heat in space. Radiators are not optional accessories, they are the ship's lungs. Even the radiators have a story because they must be large, thin, and exposed. They would be peppered by micrometeoroids, slowly losing performance, while the ship's systems age in deep cold. How do you inspect and repair a radiator field the size of a city, when the nearest spare parts are years away by light-speed communication? The payload fraction is also revealing, and it resets expectations. Even a probe payload is small compared to the propellant stack, and a crew habitat would be heavier by orders of magnitude. Add shielding, redundancy, life support, and social space, and the payload ceases to be a payload and becomes the mission. Daedalus is therefore a map of what it would take, not a plan we can execute soon, and that distinction matters. It is a reminder that fusion propulsion is a civilization project, not a single invention. You do not discover Daedalus, you build the world that can afford it. Some modern variants try to soften Daedalus with better fusion concepts, and the motivation is understandable. Inertial confinement, magneto-inertial, and pulsed Z-pinch ideas promise higher gain, better coupling, or simpler hardware. They still face the same triad because the universe keeps the same rules. You must ignite reliably, you must handle waste heat, and you must survive radiation and erosion for years, not minutes. A single successful shot in a laboratory is not an engine, and a dozen shots are not a voyage. The difference between demonstration and transportation is repetition without failure. Others shift again toward beamed power, using microwaves or lasers to heat propellant or push sails, because offloading mass is seductive. They trade onboard mass for offboard infrastructure, which can be upgraded and repaired near home. That trade works best when the payload is small and the beam is near. It becomes harder as payload grows, and as distance forces larger arrays, because beam spread and pointing errors accumulate. The further the craft, the larger the transmitter must be to keep the beam useful, and the more perfect the phase control must become. At interstellar distances, slightly off is functionally missed entirely. Now consider the idea that sounds brutally direct, almost industrial in its honesty. Nuclear pulse propulsion in the Orion lineage uses fission or fusion bombs as discrete thrust events, turning explosions into a propulsion cycle. The imagery is stark: a thick pusher plate, a shock absorber, and a series of flashes behind the ship. Within the solar system, Orion-style concepts have a real advantage, and it is not subtle. They offer high thrust and high effective exhaust velocity, which makes heavy payloads plausible, including shielding and large habitats. They also exploit a simple truth. Nuclear devices deliver enormous energy density compared to chemical propellants. If you can tolerate shock and radiation, nuclear devices compress a tremendous amount of energy into a compact package. That is why Orion has always haunted the engineering imagination, especially during the early Cold War era when nuclear testing was routine. Historically, it was both a technical proposal and a cultural mirror, our most powerful tools repurposed for travel. Orion helps where travel times are months and years, not decades and centuries, because high thrust changes mission design. It helps when you can refuel, resupply and repair within the same star system, where logistics are hard but not absurd. It also helps when you can accept a ship that is more like a fortress than a yacht. Interstellar scaling changes the arithmetic, and the arithmetic is merciless. To reach 0.1 C, you need a colossal number of pulses, or pulses of extreme yield, or both, and each choice has consequences. The propellant mass problem returns in another costume, because each bomb is propellant and energy together. You must carry the entire sequence from launch, which means the ship begins as a mountain of devices and structural mass. Then braking doubles the requirement, because if you want to arrive and stay, you need a second sequence to cancel the first. A flyby does not need that, but a human mission almost certainly does. Treaties and politics are not the main obstacle, but they are not ignorable, because engineering does not happen in a vacuum. Launching thousands of nuclear devices from Earth is a non-starter in practice, even if the physics pencils out. Even if built in space, the engineering is punishing and the operational risk remains. The pusher plate must survive repeated plasma impacts, which means ablation, fatigue, and surface damage become life-limiting factors. The shock absorbers must work for years, cycling without catastrophic failure, while the ship's structure remains aligned. Radiation is also severe, especially with fission-heavy devices, and shielding adds mass. Mass increases the number of pulses and the loop tightens because the ship grows heavier as you try to make it safer. Orion therefore illustrates a pattern that repeats across concepts. Ideas that look powerful inside the solar system collide with scaling, when asked to cross light years at high speed. Now return to the limit that most proposals try to step around, because it is where optimistic diagrams quietly become flyby missions. Deceleration is where the story either becomes a rival or becomes a passing glance. A design can publish a cruise speed and a travel time, then leave braking as a future detail. That omission is not a minor gap, and it is not a mere engineering footnote. It is the mission, because without braking you do not get time, and without time you do not get a place. The difference between we reached the system and we entered the system is measured in delta V and in years. For probes, flybys can still be revolutionary, and we should not diminish that. A fast pass can map planets, sample dust, and measure magnetic fields if instruments are designed for it, and if the data link is strong. A flyby can also scout hazards and refine models of stellar winds and interstellar medium. For humans, flyby is not arrival, and it is not even close. A crew cannot build a life in a system they cross in hours, and habitat cannot refuel from a blur. If the ship cannot stop, then every problem of survival must be solved without help, forever. Real braking options exist, but each carries a price that scales with mass, and that scaling is the hidden antagonist of this chapter. Propulsive braking demands propellant, which demands tanks, which demands structure, which demands more propellant. Magnetic sails demand time and uncertain plasma physics, because they rely on interactions with tenuous charged particles. Photon braking demands enormous sails and precise geometry, because you're using light pressure as a brake rather than as a push. Aerobraking at relativistic speeds is closer to controlled destruction than controlled capture, because the atmosphere becomes a wall of energy deposition. Even dust becomes a thermal and mechanical threat when kinetic energy rises with velocity squared. Some proposals suggest using the destination star's light as a brake with a light sail, turning the star into a natural decelerator. It can work in principle, but it requires huge sail area and careful approach, because the sail must survive heating and remain stable. The approach trajectory must be tuned so the sail catches photons without being shredded. Others propose carrying a fusion engine and using it for both acceleration and deceleration, because symmetry is appealing. That returns us to Daedalus scale propellant and reactor durability, and it returns us to the industrial assumptions that make Daedalus so sobering. When the same engine must work twice, reliability becomes as important as performance. The honest summary is simple, and it is not meant to extinguish awe. Many interstellar concepts solve getting fast, and speed is the part that looks heroic on screen. Far fewer solve stopping, and almost none solve stopping with a heavy living payload where failure is not acceptable. That brings us to the scaling law lesson, the fine print beneath every headline, and it is the most transferable insight in the whole field. What works for grams often fails for humans, and the failure is nonlinear, because complexity does not scale gently. A gram probe can be accelerated by a beam and survive as a disposable experiment. A ton-class craft demands structure, redundancy, and thermal control, because it must operate for decades without a technician on the ground. A habitat is not a scaled-up probe, and it cannot be treated like one. It is a different category of object, with life support, radiation shielding, spare parts, and governance capacity. When mass grows, energy grows with it, and when speed grows, energy grows with the square, which is the quiet trap. When you demand braking, the energy budget roughly doubles again, because you must remove what you added. The ship becomes an energy management problem as much as a propulsion problem. Then the interlocking limits stack, and the stack is why optimism must be disciplined. More shielding increases mass, more mass increases energy, more energy increases waste heat, and more radiators increase frontal area and impact risk. Each fix creates a new surface for the universe to punish. The same recursion applies to reliability, and it is not optional for crews. A probe can accept single-string systems and accept loss, because the mission can be statistical. A crewed ship must be repairable for decades, and repairability implies tools, spares, manufacturing, and trained people. Those add mass and power demand, which loops back into propulsion and heat rejection, and the loop does not care about our narratives. A ship that can truly sustain life is closer to a small world than to a vehicle. If it is a world, then it carries politics, conflict resolution, education, and continuity. Quiet systems that do not fit in engine diagrams. This is why the most feasible ideas cluster around tiny payloads, and that clustering is not cowardice. They're correctly matched to what physics lets us buy, and to what engineering can plausibly validate. Even the most optimistic near-term path to another star is likely robotic and minimal. It is a camera and a sensor suite, not a city, and that distinction should sharpen our expectations rather than shrink our wonder. Starshot could prove interstellar navigation and communication, and it could teach us how to operate at relativistic speeds. Daedalus could define the industrial threshold for fusion propulsion, and it could expose the real bottlenecks. Orion-style thinking can expand our reach inside the solar system, where time and resupply make heavy engineering meaningful, and where high thrust changes exploration. Each concept has a domain where it fits, and within that domain it can be transformative. The problem is the cultural slide from domain to destiny. A probe concept becomes a human promise, and a paper study becomes a near-term plan, because we want the story to end with arrival. The opening hook returns because it keeps happening, across decades of popular science and political speeches. We have been promised the stars for a century, and the promise often ignores the invoice. The invoice is not only energy and mass, though those are large enough to humble any budget. It is also operations and ethics, because a human mission must protect bodies, maintain ecosystems, and preserve legitimacy across time. No propulsion breakthrough automatically solves that, even if it changes travel time. Faster travel reduces some biological and social burdens, but it raises dust hazards and energy demands, and it narrows margins for error. Slower travel reduces energy stress, but it turns the ship into a multi-generational society, with all the fragility we already priced. Either way, the ship becomes a test of what we are willing to sustain. So the climax of this chapter is not that the famous ideas are impossible, and it is not that engineers have been naive. It is that each solves a narrow slice, and the full stack remains unpaid, especially when the payload is alive. The diagrams are not lies, but they are partial truths. The honest future of interstellar ambition may therefore be different from the dream, at least for a long while. It may be a long era of tiny fast probes that extend our senses, turning nearby stars into reachable laboratories. It may be telescopes and interferometers that turn nearby exoplanets into mapped worlds without sending bodies. It may be patient engineering inside our own system, where we can practice closed-loop life support, deep space industry, and long-duration governance under real constraints. And it may be a reframing of what counts as arrival, because arrival does not have to mean footsteps. If we cannot send cities, we might send information, machines, and seeds of knowledge. Transition. If the stars are not a near-term destination for bodies, we must ask what interstellar ambition is for and what it should become. The final chapter turns from designs to decisions. It asks how to hold awe and honesty together without turning physics into a belief system. We can now answer the central question without romance or despair, because the physics does not bargain with our hopes. Humans can reach another star in principle, yet the combined limits make it a civilization project, measured in institutions as much as in engines. Distance sets the scale, because light years turn travel into decades even at 0.1 c, where a single year of ship time spans a tenth of a light year. At that speed, relativistic effects are modest but real. Time dilation shaves only a little off the crew's clocks, while the outside universe still waits. Energy and the rocket equation set the cost, because momentum must be paid for twice, once to leave and again to arrive. For rockets, that payment means reaction mass, and the exponential penalty grows brutally as delta V rises. For beamed propulsion, the payment shifts into power plants, optics, and pointing accuracy that must hold steady across astronomical distances. Braking and hazards set the difficulty, because arrival is not a postcard moment, but another full burn, another 0.1 c to erase. If you do not brake, you do not visit. You merely flash through a new system in hours, watching planets slide by like sparks. Meanwhile, impacts turn dust into shrapnel, because at relativistic speeds, even a grain of sand carries the punch of an explosive. The interstellar medium is thin, yet over decades the odds accumulate, so shielding, forward debris clouds, or sacrificial bumpers become part of the design. Ecology and humans set the fragility, because closed life support and governance must work for generations, not for a heroic season. A habitat is not a capsule with supplies, but a living system with carbon cycles, nitrogen balance, microbes, crops, and failure modes. The hardest problems are often quiet ones: slow leaks, creeping contamination, and the psychology of confinement that can erode cooperation. That synthesis is the verdict. Interstellar travel is not a startup problem, and it is not a single breakthrough away. It is the kind of undertaking that once built cathedrals and canals, projects where the builders knew they would not see the end. A narrow path still exists, and it starts small, as it has so often in exploration history. Tiny robotic probes can plausibly reach nearby stars first, likely as fast flybys with extreme autonomy, because mass is the enemy of acceleration. Think of gram-scale craft pushed by light, or compact nuclear systems that trade comfort for speed. Machines that can be risked, iterated, and replaced. They will test navigation when the target star is a moving point, relativistic dust damage on real materials, and deep time communication where faint signals must be pulled from noise. Human missions demand stacked breakthroughs, not one miracle engine, because every subsystem must survive the same long timeline. Propulsion must be high exhaust velocity with industrial reliability and a manageable waste heat, since gigawatts trapped in a hull become a lethal furnace. Radiation protection must be practical in mass, and still protect brains, fertility, and electronics from cosmic rays and solar storms. Closed ecosystem must be actively managed, buffered, and repairable for centuries, with redundancy that is biological as well as mechanical. Long-term governance must preserve legitimacy, consent, education, and non-violent conflict resolution under scarcity, because a ship is a polity with no exit. This is where anti-hype becomes pro-science. Honest constraints prevent disillusionment, and they redirect ambition toward milestones that compound, like scaffolding that stays useful. Build interplanetary habitats that practice closed-loop life support and social continuity, where small errors can be found before they become fatal traditions. Develop fusion for power and propulsion components, even before fusion rockets exist, because high-density energy changes everything from shielding to manufacturing. Improve radiation biology, shielding materials, and artificial gravity experiments, since we still do not fully understand how decades of low gravity reshape bodies. Invest in planetary defense, because staying alive on Earth is the first interstellar prerequisite, and because impact preparedness is a test of long-term coordination. Somology explains why we keep telling Starflight stories, even when the ledger is unforgiving. They promise secular afterlives through legacy, transcendence, and species continuity, offering meaning that outlasts individual lifespans. That impulse can inspire real engineering if we refuse to turn desire into false timelines, and if we treat wonder as motivation rather than evidence. So the dream changes shape. The stars are not an escape hatch from Earth. They are a mirror that clarifies what we value here and what we are willing to maintain. Our planet is rare, our solar system is large, and the reachable future is still enormous, even before we touch another sun. Look up and hold both truths at once. The night sky is an invitation, and it is also a boundary drawn in light years and in biology. In a time-lapse, constellations drift while the Milky Way arches like pale smoke, beautiful, indifferent, and precise. Or deepens when we accept the universe on its own terms, then choose wisely within them. We began by shrinking the romance and enlarging the map because 4.24 light-years is not a hop, it is time made physical. The 5 hard limits kept returning like gravity. Distance sets the schedule, the rocket equation and energy set the price, and breaking demands you pay twice. Then the universe added its quiet violence, dust that becomes shrapnel at a 10th light speed, radiation that never clocks out, and a ship that must be both fortress and garden. Inside that garden, Biosphere 2 reminded us that self-sustaining really means actively managed, with buffers, sensors, interventions, and constant humility toward non-linear biology. Finally, the hardest payload turned out to be us, because bodies age, societies drift, consent frays across generations, and governance becomes a life support system as critical as oxygen. When we audited the famous solutions, the pattern was consistent. They can buy speed, or they can buy mass, or they can buy survivability. But the full invoice rarely gets paid in one design. Starshot shows how far information can travel when you shrink the traveller, and Daedalus shows how heavy a serious attempt becomes when you insist on a real ship. Somology ties these chapters together by explaining why we keep reaching anyway. Starflight is not only a destination, it is a story about continuity, legacy, and what we refuse to let end. So the revelation is not that the stars are unreachable, it is that reaching them requires a civilization that can manage energy, ecology, and ethics for longer than a human lifetime. Interstellar travel, as we imagined it, was never just propulsion. It was a total systems test of physics, biology, and governance under the pressure of time. So, are we physically capable of sending humans to another star on any meaningful timescale? Or does the universe forbid it in plain physics? Physics does not forbid it, but it does something more demanding. It sets terms so steep that meaningful becomes a question of definitions, priorities, and patience. If meaningful means a crew that arrives within decades, lands and thrives, then our current tools are not merely insufficient, they are pointed at the wrong scale of energy, shielding and closed-world reliability. If meaningful means arrival as knowledge, as instruments that cross the gulf and speak back, then the path is already opening because small machines can accept risks that living worlds cannot. The nearest star is still a sentence, but now we can read it clearly. It is written in delta V, waste heat, cumulative dose, and the fragile legitimacy of a society that cannot turn around. The question then is not whether the universe allows interstellar travel, but whether we can become the kind of species that can afford it without lying to ourselves. When we replace hype with honest awe, the stars do not get smaller. Our responsibility inside the reachable universe gets larger. Build the habitats that teach us closed-loop humility, master the energies that do not poison their makers, and design governance that can hold consent across time. Because that is what a starship really is. Perhaps the most profound first interstellar mission is not a launch date, but a culture that can keep a promise for a century and still call it freedom. And if we never walk beneath another sun, the work is not wasted, because the same disciplines that could carry us outward can also keep us alive, together, here. The brutal reality is not a door slammed shut, it is a mirror held steady, asking whether our dreams can mature into commitments. So aim your wonder at the next honest rungs: radiation biology, artificial gravity, closed-loop habitats, fusion and beamed power components, and resilient institutions, because every solved constraint is a small piece of tomorrow's sky.